What's up, people? Getting rid of the awful .NET standard library? Well, it's not about .NET. We're not that bad. Wait. Okay, I should have looked at the if-def. What is this? If defined. I guess this is better. Okay, this is if we have a bit scan reverse intrinsic, I guess, right? Okay. So we don't have that right now. We also need CLZ. I don't frickin' know. I don't know. Count leading zeros is what that is. We don't frickin' have that either. We can write it and it'll be very slow. And then that'll be motivation to make it intrinsic. Imagine making an entire engine in JavaScript. I mean, that's what a lot of people these days think is good programming. Like, people think JavaScript is the future because it's the web, man. All right, we don't need max 32. We don't need this either. For us, that's just a legal cast. Okay. We need this status. We don't know what that is, but so this is only for float 32, though. This guy doesn't have a float 64 version. Because I don't think this is the main point of this library. Yeah, I know that there are instructions to do that. The thing is, the compiler does not have an intrinsic that it understands means count leading zero. It does have, oh, it's S to D, right. I hate that naming convention, dude. Okay, great. Okay, so we will proceed, and then we will all right, we'll proceed, and then we'll look at, after this works, we'll look at S to D or whatever. Okay. Okay. See, these are int. What does int mean? Why am I putting equals 0? It's like I start, okay. Why does it say equals 0 and then buffer sub I? All right, maybe that's pasted out of the loop. It like doesn't cut leading spaces, I guess. Int means give me a number, I don't care about bits, except you do care about bits in this application, because if I'm porting it to something, I need to know how big those things need to be, right? Okay. Like in something tight and tweaky, like a string to float, it's like, all right. I mean, it's fine. Wait, dot index. Oh, that's goofy. I see what they're doing. They're just setting these, like, put some documentation. These are being initialized to indices out of range of the string, just so that we know when we set them. No check-in, make these -1 probably. Like, because it's a little bit, you know, you have to compare it to a non-constant. I don't know. It's not that good. So this is just saying, was a dot already found? Like, come on, man. That's the other thing is, I mean, maybe we're going to have to see how clean it wants the input to be, because we probably want to modify that or put a front end onto this or something. Okay. Anyway, so M10 digits. Okay, well, okay. Wait, what was, hold on. M10. Oh, these are Mantissa digits. These are Mantissa base 10 digits. Okay. I like that mantissa and exponent are the same length of word. Signdem is true is incorrect. You think it should be colon equal? No. No. Len doesn't exist. Yeah, that's the count. So I was just in the middle of thinking about that, right? Yeah. This is just like, did we set this? And I'd prefer that to be -1 probably. Okay. So we're here. And then all this is inside the for loop. Sometimes it's easy to lose track because the indentation doesn't match and I'm changing it. Okay, the mantissa, we multiply it. This is exactly what Sean's code did. It's like the obvious thing that you would do. All right. Okay. So either we get to the end of the string or we hit no, we get to the end of the string. Oh, or we hit a character that's not a dot or 0 to 9, right? Okay. If it's not a dot or 0 to 9, it could be an E. We loop. We stay in the above loop until we hit the end of the string for a digit that is not in 0 to 9 or dot. If it's an E, we do. Okay. So if it's an E, see, this is, okay, I see why he did this. All right. We need that. So if it's an E, we set the E index. And then it could be plus or minus. So the reason this is structured is that if it's not an E, or it's not a plus or minus, we just will fall out eventually, and then we'll hit this, which is fine. Okay. This is a lot what you would expect. Okay. Where are we? I got parentheses wrong. Okay. Okay, so it's not called buffer. It's called S. Okay. So we could use default return values here. Let's do this. Because saying return 0 all the time is a little bit of a hassle. Okay. So if you have an E and maybe a plus or minus, so len, you know what? Let's just that's fine. Okay. So if E10 digits is greater than 3, all right. I always feel like this is a weird way to structure this. So this piece of code here, everyone does it this way. Maybe there's a reason, but I don't understand why you don't do it like this, right? Okay, so instead of testing it against ASCII and then doing this, like, why don't you just go here minus the 0, and you say if it's less than 0 or greater than 9, right? And then you're there, right? That just seems better. And I guess the answer is, if you're actually testing several things in the loop, you don't want to do that. So maybe this one up here, like this one up here, you didn't want to do that because you don't want to be confused about this. Although you could do crazy things there, but yeah, I mean, I guess that's why, is so that you can do it everywhere. All right. So if there's too many exponent digits, otherwise we keep doing exponent. All right. All right. Okay. So we have our exponent. We have our mantissa. Oh my God, guys. All right. Like what? Let's not, like, a thing where you minus equals 0, otherwise, like, I just, no. If dot index is less than E index, E10 minus equals E index minus dot index minus 1. Like, look, only subtract if, like, this subtract 0. I mean, I could see why you would think you would want to write it this way, because maybe this evaluates into a branch-free thing, whatever. It doesn't. Doesn't matter. Doesn't matter. And the compiler is probably going to do that anyway. Okay. If M10 is equal to 0, why are we, okay, return 6.success. I don't know if we correctly parse -0. We're going to have to check that. I mean, like in the actual compiler. I feel like that's something I would have done correctly, but I'm not sure. It's worth thinking about. And in fact, okay, no check-in. Verify that -0.0 works. Also verify that -0 coerces to -0.0, keeping the minus sign. So there's two potential failures here. One is that we don't parse the floating point number and keep the sign bit. The second one is that maybe when we parse it as an integer, we don't keep the sign bit. In fact, we probably don't. This probably doesn't work. And we should probably make a test for that. Okay. I don't really want to keep like printf debugging in there. We can use logging or something. So we're going to consider what to do with that later. Number is less than 1e minus 46, which should be rounded down to 0. Okay. Great. Okay. Oh, int 32 bits to float. All right. I'm glad he put these comments in. These are very helpful comments. All right. I kind of don't know why signed M is not U32 to begin with. Instead of bool. We don't really use, Okay. So we're going to say signed M is 1. And then down here, we don't have to cast it. Okay. Convert to binary float mantissa times 2 to the exponent while retaining information. Okay, this is weird. Oh, right. I kind of remember. There's some weird stuff going on here. All right. We're just going to work through it and see what's happening. So what's going on with the... All right. This is kind of a half-baked Emacs mode. Oh, we're missing a paren. Let's check that. That looks weird. Okay, yeah, you don't want to, right, obviously you don't want to OR this into the shift, right? Okay. Or it into the amount that you're shifting by. Okay, the length of M is the log base 2 of M times 10 to the E10. Right, that makes sense. We want to compute floatman. So it's log base 2 of M10 plus E10 log base 2 of 10, right? That's just your standard logarithm identities from high school, right? Which is log base 2 of M10 plus E10 plus E10 times log base 2 of 5, right? So, right, that's because 10 is 5 times 2, right? Log base 2 of 2 is 1. So this is 1 plus log base 2 of 5, and so you factor out the 1 times E10. There you go. And log base 2 of 5 is obviously a constant as well. Okay. So that's pretty straightforward. I know that math. Whoops. Was that the name of that variable, U32? Hold on. E2. I just got confused. These are E2 and M2. Sorry people, sometimes my brain doesn't work. All right. So binary output exponent of blah, blah, blah. And this just tells us how long to go before we stop, I believe, right? And check the rounding. So he says you want to compute the float mantissa bits plus 1 for the topmost bits, right? That's because that's all that fits in the number, right? Computing more than this will not be useful because there's nowhere to store it. right? So we therefore choose a binary output exponent of this, right, minus this. Okay, by binary output exponent, I guess that means I mean, this is, I'm not sure what he means by binary output exponent. It's probably covered somewhere else. But anyway, so that's how many bits do we need to represent the number, right? Minus how many can we actually fit. Oh, this is just, okay. This is the right. This is the exponent inside the floating point number. Yeah. And so it's, you know, yeah, great. Okay, so we use floor log base 2 of 5 to the E10 so that we can get at least this many bits. Better to have an additional bit than to not have enough bits, for sure. That is true. Okay, so E2 is floor log 2 sims E10. This code's pretty good. Like, I understand it. It's pretty clean. It's not doing anything bananas. So I dig it. Doesn't look like it came out of Microsoft, which is good. Okay, so we now compute M10, the Mantis in base 10 times 10 to the E10 divided by 2 to the E2, right? Which is a rejiggering of some of these factors. Well, I mean, okay, so this is this. I don't know why we're computing exactly this without thinking real hard about it. Ten to the E10 divided by 2 to the E2 is, okay, this is like, this is just the exponent, right? So E10 is a number like 17, right? And 10 to the E10 means 10 to the 17, which is like the actual magnitude that you mean to express, right? And then 2 to the E2 is the same, but in base 10. I guess this has to do with rounding somehow. I'm going to not worry about it yet. Sometimes second pass, right? E2 minus E10. All right. These constants are obviously defined somewhere else. So this is going to be weird because I don't want to port over all this code right now, and I don't want to maintain the file structure that he has of many files and stuff, because I want this to compile fast. So I guess I'm just going to start piling it all into one file here and just say, if you want to port the whole thing later, which is probably a reasonable thing to do, then just rejigger it a bit. All right, because we're going to need these constants and these routines and stuff. Okay. We also compute if the result is exact. Okay, right. Oh, so the brackets here, the brackets is like the floor, I guess. Or the rounded. I don't know what that means. I don't do enough numeric stuff. But so this is like probably rounded to nearest is the brackets, right? So exact result, of course, means rounded nearest is equal to no rounding, right? Okay. This can only be the case if the 2 to the e2 divides m10 times 10 to the e10. Right, obviously? Wait, is that obvious? If 2 to the e2, well, yes, because that means this is an integer. Which in turn requires that the largest power of 2 that divides m10 plus e10 is greater than e2. The largest power of 2 that divides m10 plus e10 is greater than e2. I kind of like if 2 to the... That's like applying log base 2 to this, sort of, right? Somehow, I quite kind of... I would need to think about it. If e2 is less than e10, then the result must be exact. I mean, yeah. I mean, that follows from what's earlier. How do you get e2 less than e... Oh, I guess if it's negative. Wait, no. That doesn't make sense. I'm a little confused because I'm not sure under what condition e2 would be less than e10. So e10 is the exponent written in base 10. e2 is the exponent written in base 2. The exponent written in base 10 should pretty much always be less than or equal to the exponent written in base 2. So I don't understand that right now, unless I'm being dumb. The exponent can be negative. I mean, the exponent of a... Sure, any number could be negative, but I don't think... So if e2 is negative, e10 is going to be negative, right? I guess so. I guess that's the case that we're talking about. I just don't understand why the exponent being negative would change the divisibility. A number can be divisible by 2, yet not by 10, so m10 can contain additional powers of 2 as divisors. Right, but that's not... Well, m10, right, but we're talking about the exponents right now. Not the mantisses. Okay. Well, and plus, so this is, I don't get it actually, right? Because this is all in E10 greater than or equal to 0. If E10 is greater than or equal to 0, E2 is also going to be greater than or equal to 0. This is fun, you know, it's, in my opinion, it's okay for me to not 100% understand this right now. Because sometimes the way I do is I take multiple passes at things, right? So I can just keep on cruising through, you know, as we port these little subroutines and stuff, we'll see how our understanding evolves. They say largest power of 2 that divides M10 but that's not E2. That's some extra number, right? E2 is a different thing. Anyway, let's keep going, and we'll evolve our understanding. Okay, M10 times 10 to the E10. This is doing the same thing, but for negative exponent case. Which is different for some reason. Maybe because of the domains of these functions. You know, at this point, this is probably where you're better off reading the paper than trying to figure it out directly from the code. Oh, hey, Sean's here. The E2 less than E10. E2 gets minus float mantissa bits. So assume there's some narrow range. Yeah, I feel like this is a weird special case having to do with rounding or something. I don't know. I don't quite get it, honestly. Okay. So, well, we're getting toward the bottom. And then we'll port all the things, and then we'll test it in a little bit, and then we'll do the 64-bit. Okay, compute the final IEEE exponent. Wait. All right. I was about to... So my mouse is distracting me by running out of battery. Let's plug that in. So this is signed, right? Okay, this is signed 32. Yeah. Whoops. Okay. If it's greater than FE, then yeah, we're not doing okay. So if signed M returns success float 32 infinity, whoops, like that, right? Or we could do, whoops, return success if signed M, then minus float 32 infinity else. I know we define that somewhere. We'll just put declarations in there, right? Let me see. Where do we... Yeah. We don't want to assume that that gets used, so... Oh, well... Instead of saying minus and force... I don't know which one's cleaner, man. Whatever. Anyway, that's a lot cleaner than composing the number like he was doing. You know what? We're going to want 64-bit eventually, so let's just get those. Let's just get those. Come get some. Like, people think that infinity just blows your mind and it's such a huge number. And there's all these paradoxes, and mankind will never fit infinity within his brain. No, infinity is not that high of a number. It's just 7f80, 0000. There's no Zeno's paradox there. It's only, infinity is 8 digits long, guys. All right? 8 digits. Like, come on. Yeah, if you count the 0h, it's 10 digits. That's true. And 10 digits is a lot more than 8, but it's still within the realm of what we can handle. Okay. We need to figure out how much we need to shift M to. The tricky part is we need to take the final IEEE exponent into account. So we need to reverse the bias. All right. If the exponent is 0, then we shift by 1 bit because that's the implicit bit, right? You know, I don't know, man. This is... I feel like I would prefer to refactor this, but okay, whatever. To round up if the exact value... Round up if the exact value is more than 0.5 above the value we computed. Yeah, Sean, so in the earlier stream today, I started doing the, because we're just trying to replace the float parser because we're calling out to libc right now. So I looked at, I thought there would be one in like STB scanf, but that's only scanning and not printing, I guess, right? So then there was one in your C Lexer, but that didn't look like it was trying really hard to round exactly. So I ended up over here. Of course, the point of this library is also mainly printing, right? And we're not worried about printing right now. We're worried about, wait. Yeah, we're worried about scanning. Anyway, I'm confused about what I was going to say, but this isn't the main point of this library, but hopefully it's a straightforward port of something that's reasonably good and battle tested, and it does look like it's trying to round. So we're doing this. I'm not a fan of goofy, weird names for code, but it is what it is. All right. So we're back here. Trailing zeros is some stuff. We don't have to say 1U. Well, maybe we do in this case. I don't know. Because that'll turn into an integer otherwise. Like, what? What is this? Trailing zeros and equal. This is a bool, right? I spelled it with an E. Because I just wanted to. It's probably stupid to change the spelling, but whatever. Okay. Do I even have ampersand equal? I don't know if I bothered to implement that. M2 and 1 left shifted by shift -1 minus 1 is equal to 0. So if that's equal to 0, then we end with true. Otherwise false. I would just put an if statement here, dude. I feel like his coding style is he's trying to avoid if statements in order to get the compiler to avoid branches. But like using some of this stuff doesn't mean the compiler doesn't generate branches in the intermediate representation anyway. So I'm not sure why be so cryptic about this stuff. I would just say if this, then trailing zeros equals false. That's way more readable to me. It's still crazy because of the math, but it's like not super bananas. Yeah, it should be taken into its own I mean, this is just spam. This line of code is just spam as far as I'm concerned. Like, for the most part, I said this was clean and didn't do anything bananas. If it all looked like this, I would delete the file and start over. Like, it's just not the case that this is going to make the compiler generate better code. That's not how it works. I mean, although I don't know, maybe he tried it on specific compilers and it happened to, but eh. Okay. I'm just going to change this. Okay, chat, you've got to have my back because we haven't compiled or tested this code yet, and we won't yet because we have to port all the routines, right? So we're and equaling this, right? And this is a bool, so this can only be true if this is true, which means, okay, let's do it one step at a time. We're going to say if this is not equal to 0, trailing zeros is false, right? These are equivalent, right? So if this is equal to 0, then it stays true, which means we don't change the value, right? Or not that it stays true, but it stays its own value if this is equal to 0. If it's not equal to 0, we set it to false, right? So if it's not equal to 0, we set it to false, which is equivalent to just getting rid of the not equal to 0. Right? And ditching a paren. That is way more readable to me. I still don't know what's going on there, but it's more readable. You would do this kind of blind refactor one step at a time, never mind. Yeah. I mean, what you really want is to have a big test for it, but okay. Okay. I mean, I guess there's something to be said for, like, we're trying to create branch-free code in the case where the optimizations are turned off. But like that, by the time you get to debug code versus release code, like having a branch ain't gonna matter. That's not what makes your code slow or fast, I don't think. Okay, anyway, not on modern CPUs. Do compilers dislike shifting out that stuff from the brackets into separate variables? Not really. I mean, it depends, but probably not. The reason why I didn't factor this out is I don't know what to call this. I don't know what is a good name for that. Right? It's obviously, so it's 1 left shifted by shift -1, -1. So this is like a mask of some kind, right? And obviously, because we're bit masking it. So this is like, right, anytime you take a power of 2, which is this, and subtract 1, you get all 1 bits below the power of 2. So this is all trailing 1s and then 0s up top. Right? So we could do that. Okay. So, last removed bit. I don't know if these, wait, isn't M2 a U32 already? So M2 is a U32, so we actually don't need that. Okay, mantissa in base 2 right shifted by the shift -1 and 1. Right, so this is like, so right shifting by shift -1. Oh, wait, shift is a right shift. Yeah, okay. So this is actually saying, are we gonna shift any bits off? If we are, then don't write any trailing zeros because we're already rounding. Right? Does that make sense? If we're rounding some stuff off the end, then we obviously don't need zeros at the end. Zeros are for when it's exact, right? Okay, this makes sense to me. And then this just says, okay, what's the last bit that we're gonna shave off, right? So, and then do we need to round up? Well, if it's a 0, we don't need to round up, right? So last removed bit and no, right? If there are trailing zeros, then we know. I don't know. This is a little bit weird. And like this, you don't need this not equal to 0. This'll cast to bool. So like you can just say or this. I mean, that's actually true here as well. You don't need this not equal to 0. Watch me break everything by doing this. Okay. We're almost there. We're not going to need this. So IEEE M2 is M2 right shift plus roundup. Like, what's the precedence on left shift? I don't think it's necessary to do that, is it? I think we kept. All right. Whoops. Rounding up may overflow the mantissa, right? In this case, remove a trailing 0 into the exponent. Right, so this just, okay. I'll trust them on that. I don't remember why you can add one and not worry about this. I guess infinity. What's the exponent for infinity? It's like max exponent, isn't it? Anyway. Okay. So we raise the exponent by 1. IEEE is this. Okay. Look at all these parentheses. It's like Lisp. Signed M. Left shifted float exponent bits, right? Wait, what? Oh, signed M is whether the mantissa is signed. Okay, so that's... We OR that with the exponent. Oh, this is just a signed bit, right? Sorry, I was confused. So this exponent is in the bottom of the integer, right? But then we're turning on the sign bit by ORing that with the thing. And then we're shifting it by the, yeah, okay. So this all makes sense. If you know IEEEs, this all makes sense. All right, great. Ship it, except no, because there's all these functions that we don't have. And we probably made 10 zillion mistakes. Oh, we don't have plus plus in this language. I debate adding it sometimes, but I'm just trying to be kind of minimalist right now. Okay, we don't FU in this language either. Like this is going to constant expression evaluate to an integer no matter what, but not an integer of any type. It's just an integer, right? So this is just like any constant that you would write. So you don't have to put a type on it because its type will be determined by this, which is, right? We made this U32, right? Oh, we have to check. Because I did this, we have to check to see if that makes any shenanigans or if it simplifies anything else, right? Okay, we don't have to cast that to U32, which is great. We probably do there. No, that's a U32 also. That was U32 in his code. Why is he casting that, bro? He has some extra casts. All right. Wait, what is M2? Okay, that's also U32. Which means IEEE M2 is also U32. Right, okay, so that's fine. Maybe just update E2 with the sign bit in the separate line. You mean this part? Just say IEEE E2 or equals. Yeah, that'll make more sense, right? So instead of this, we're going to go the E2 in IEEE or equals signed M left shift exponent bits, right? Okay. And then this is this left shifted by the mantissa bits, or yeah, like that is pretty self-explanatory, right? Like if you know floating point numbers, you look at that and you don't even think about it. Whereas this is like, I trust you that something's happening. So is that what you meant, Sean? I like this better, for sure. Can you explain why IEEE isn't returned directly? Because it's an integer and we want a float. And he does shenanigans in C++ to convert that integer to a float because it's not legal to do this in C++, but it is legal to do this in our language here. So we are doing it. Or maybe, like, we should just introduce like a bitcast operator, but we don't. So if that doesn't make sense to you, why is this an integer? This is an integer because we're creating an integer that has all the bits in the right places that the floating point number would have. You dig it? Yeah, I'm taking the pointer of IEEE, casting to a pointer to float, and dereferencing it. I feel like it's 1996 and I'm programming my first video game again. And we're like, not my first video game, but my first professional video game. And we're like trying to get into float faster without going to the FPU. Actually, float to int is really what we would do. Oh, the old days of float to int, of adding the magic number to do the thing. Unary plus for bitcast. Can I give some intuitions for when the compiler is able to optimize away something like an if branch? Optimize it away? So in general, compilers these days have a lot of machinery for trying to boil down complicated expressions to like seeing what's actually not actually necessary, right? And reducing complex expressions to simpler expressions. And a lot of those are like, branch around this thing that does something. Oh, wait, that thing doesn't actually do anything. So we can get rid of the branch, right? Compilers just have a lot of stuff like that. And they generate a lot of stuff like that internally when they compile your code. And so being afraid of adding a little bit more, well, afraid is the wrong word. Like using question mark colon a lot because you think that's going to generate a C move when an if statement wouldn't. Is like, no, look, question colon is probably implemented as a branch almost always anyway, I guess. I don't know. I should look at the compilers to see, but maybe that's not true, but I feel like it is true. Anyway, then it's debatable about in which cases you should even use CMove for things versus branches. Branches are really fast on modern CPUs. And so in general, I would say if you don't absolutely know that it's guaranteed to be faster most of the time, make the readable code. Because readability actually leads to speed in the long term. If you think long term systemically about all code everywhere, right? Right now, we are in a case where the world is drowning in a lot of code that most people don't understand most of because it's abstracted under 17 layers, and that mostly doesn't work, is mostly a lot more complicated than it needs to be to do what it does, right? And so time that we spend dealing with bugs, right, and just understanding how to use code that's hard to understand, and all that stuff, that is time that is taken away from optimization, right? Or maybe rewriting the code that calls this library code to call it in a better way, which is a different form of simplification and often optimization, right? And so there's actually, if you look systemically, there's a trade-off between understandability and speed, right? So if you think, oh, I know this is going to be like 0.001% faster if I do the question colon, that's actually probably, that's almost guaranteed to be wrong from a systemic point of view, because if people understand it better, code on the whole will be faster. Actually, and then there's one more thing, which is like if you do crazy stuff that takes longer to compile, even a little bit, that definitely adds up in the long term. And the more time you spend waiting for things to compile, the less time you spend making code simpler and faster, right? So I think you need to make these trade-offs in a global sense, and people are not used to thinking that way. You're using like question colon because sometimes it makes code shorter and easier to read. Yeah, I get that. Like, I'm not saying don't ever use question colon. I'm just saying don't use it for the wrong reason, right? And especially don't use it when it makes things harder to understand, which is often. Okay. Okay. The minus equals 0 with question colon was pretty bad. Yeah, I agree. I mean, to be fair, most of this code isn't like that. It could have been a lot more like that. All right, so let's start seeing what we need. Oh, int j, this isn't C, right? I feel like there's going to be a number of type casting problems that we're going to have, because some of these are signed and some of these are unsigned maybe, and it's not that disciplined. All right, we need status, which I think we can just make at this point, right? We're going to make it a U32. Why? Because Mickey Mouse. Success. Let's make success. I mean, should success be 0? I guess so. That's very Microsofty. And then invalid. Oh, input too short, sorry. Not too long. Malformed input. I don't know. Oh, that's probably the assert before it has too many parentheses. Right? Or not. Let's get rid of this. There's just too many parentheses going on. Although I honestly don't know what that precedence is, so let's just leave it. Okay. Maybe I just don't have that operator and it's a bad error message. Input too long. Oh, we do have a too long. Loss of information in operator minus equals left type S32, right type S64. So e-index or dot index. Okay, that's because this is a string and we're not putting a limit on the length of the string, right? Which we don't want to. Like you could put you could put a 5 GB text file in here. So the question mark that we have is, do we want to cast? All right. This whole thing about maybe he didn't want them to be signed. Here, let's just do this. If s.count is greater than or equal to, like you really shouldn't, like you kind of want this code to return the character after it's done, which I guess it wasn't really made to do, and all that kind of thing. So we may do that. It doesn't seem like this is intended as a user-facing string to float. Yeah, it probably isn't. I don't know. Do you know of a different one? Should I start over and port a totally different one? Because this doesn't have any options to it, right? Maybe we don't want, because it only accepts 8 digits of mantissa. That's a good point. Do I need to use Jeff's version? That's what I was going to do. Jeff emailed me, I think, his string to float like frickin' years ago, and I just never got around to it. It was like RR scanf or something. And I can't find that by searching my email, so. Oh, R sprintf. Oh, he says he doesn't. Okay. Maybe I'm remembering that wrong. And then here's a thread from me talking to Sean in 2016 saying there's no STB scanf. That must be the first time I came to look at this. And I found the STB clex or parse float. And Sean said, don't use that. Well, maybe I just use what we're using. String to float is really hard and you don't think Jeff's is valid. Voice chat. Okay, let's do a voice chat. That'll be fun. We haven't done this in a long time. Let me give me about 1 minute. All right. Oh no. Discord wants me to log in. Like I remember any of this stuff? It's asking me to select all images with a fire hydrant. And then it keeps putting more up when I click on them. Like, what? And then it says my password isn't... Okay, this is why I rage quit Discord before. Every single time I try a password, it's giving me a zillion things to click on. There's no other crosswalks, guys. Okay, there. God damn it, dude. Now it's giving me bicycles. There's no bicycles. What do you want from me? This is why I rage quit. My account has been hacked. No, it hasn't. My account is fine. I have it on my laptop. Oh my God. Fuck you. Okay, Sean, can I talk to you on Steam or whatever? I'm never logging into Discord again. Like, how many does it want me to do? That's completely stupid. There's no way I'm going to use your time-wasting chat app if you're just going to keep throwing these at me. It's like, look, I don't remember which password. I need to try 7 or 8 different passwords in order to log in. You need to let me do that. If you don't do that, I can't use you. You know what I mean? That's so offensive, what they're doing right there. It's Google thinking I'm a bot. Well, that's not my fault, okay? What? You're on Steam. All right. Steam. Now we have to update Steam. Oh, what's it going to sell me now? Oh, I've received a gift from Casey. I'm adding it to my library. June 25. It's the summer sale. I hope I remembered to put the Witness on sale. Oh, I did. Look at that. $9.19. How do I answer Sean? Was that not the phone ringing? Hello?
Yep.
Oh, hold on. I got to make you go out the... Wait, I have... Okay. Can you say something now?
Testing, testing.
Okay, good. So it's actually going into the earphones. What's up,
You have
man?
the earphones
Okay.
on? I can't even see.
I have one in one ear.
Oh, I see. Yeah.
Yeah, I'm styling the earphones.
Okay. So, because this is also for chat, so I
Yeah,
wanted to summarize stuff you may know, right?
totally. Totally.
All right. So, in the good old days, there was this sort of best effort where you just tried to make sure, we're talking about both string to float and float to string, you just, made sure it basically worked. So specifically, the thing that has happened since is everyone has been like, let's just actually return the right answer if there is one, no matter how hard that is to do.
Yep.
So on string to float, okay, so let's clarify something. Base 10 and base 2 are compatible in the sense that fractions of that have only a power of 2 in the denominator are exactly representable in decimal. Like, 1/3 is not exactly representable in decimal. It's infinitely repeating.
Yeah.
Um, so, but 1/2 is representable, 1/4 is representable, and floating point numbers are always a numerator that's arbitrary and a denominator that's a power of 2. It's a huge power of 2 or whatever. So it is the case that any floating point number is exactly representable in decimal. So people settled along this idea that if you do float to string and you ask for 1,000 digits, it should give you the exact 1,000 digits that exact floating point number is. Even though there's not very much use to that.
Yeah.
And it's also a little debatable because a floating point number can also be thought of as representing a bucket, a range of values between, the epsilon or half epsilon. The difference,
Yeah.
the distance between two floating point numbers is some amount. And so when they fall in between, they're going to round to one or the other. And you can therefore think of the number itself as representing that bucket. And so you could argue that, let's output any number that's in that bucket. It's fine. And so there was a classic strategy for this where we output about 8 or 9 decimal digits and then just all zeros. I think that's what Jeff's code does. It may do 16 digits or something and then be all zeros. So that's his float to string code.
Yeah.
That's the easy case. Okay, so the hard case is string to float because everyone said, let's do the exact same thing, which means if you give me, you can take one of those numbers with like 1,000 digits or whatever. There's some limit to how many digits you can do because you're a fraction over 2. And so, you do 2 to the 1,000, 1 over 2 to the 1,000 has some large number of decimal numbers, but not infinite. There's some limit, and you can figure out a limit based on the actual size of the mantis of the exponent. But anyway,
Yeah.
So the actual thing here is like if you output one of these really long numbers, that's the exact value of that floating point number, and then you like increment your floating point number to the next largest value and print that out. Here are these two numbers with a lot of digits at the end, but they were distinguished in the first 9 digits. And you pick the number that's halfway between those two things, and print that out to 20 digits or to 1,000 digits rather, because both of those other numbers were 1,000 digits. So you have like 1,000 digits of precision. Print out that number that's exactly halfway between them. Take that halfway between and round that last number, or not round that number, increment or decrement the very last digit. The modern way of doing string to float says we have to scan all the way down that string. That number lies right on the boundary point between these two floating point numbers. We go all the way to the end of that string. We read that last digit. We decide which way it falls in the two buckets. Does it fall to the left or to the right? Yeah. Okay. So what that has meant is that correct string to float has required something like a big number representation, is how people have traditionally implemented that. Yeah. They've just said, well, let's accumulate all of that mantis and make it go. And then there have been algorithms that tried to let's just leave it in string form instead of the big num. Let's see if we can just go back to the string and be smarter about it or whatever. Yeah. And Jeff's stuff just doesn't touch any of those issues. All he cares about is that it falls in the right bucket and therefore it round trips.
Yeah.
So that is my whirlwind summary of the whole thing.
And also, when it comes to libraries that shipped with compilers, for a long time, Visual Studio did not do what you're describing, for example.
Exactly.
Right?
Exactly.
But at some point, they switched over, I think. Anyway.
Okay. So somebody in chat is making this comment, and they're correct. So it's a little more complicated because there are two kinds of float to string. There's a float to string algorithm which tries to produce the shortest thing, which is its own, which guarantees you sort of a finite length thing. But there's also when you do a printf and you say printf and give me 60 decimal places.
Yeah.
And those two actually require different algorithms to implement. One,
Yeah.
like the one has to do all the crazy extra stuff, and the other can stop faster.
Yep.
So that's the state of that, and that's why there are no good solutions to this problem generally, because everyone's settled on doing it the hard way. That the way we should solve these problems is we should correctly solve that weird boundary case,
Yeah. That
and
annoys
that
me a
therefore
lot.
and that therefore, well, they part of why they settled on it was because they found algorithms that would not have to be slow if you don't force them to. Like, if you don't ask for 1,000 digits on the output and you don't feed in 1,000 digit input, it doesn't have to be slow. But they did it by complexity. Like some of the famous algorithms like Grisou or whatever are things where it's like, oh well, this handles like 99% of cases, and then you have to fall back to the regular code in the other cases. So that's how they get their speed, is they do a lot of that kind of stuff, which is a nightmare in terms of complexity. Yeah.
Yeah. Yeah. And I'm almost, I don't know exactly how to think about, like, I can see why people would argue for one or the other, right? So from my point of view, it's like, hey, we're making this whole new code base, right, with whatever the standard library, quote standard unquote library, which isn't really going to be a standard library, but whatever. The code that we give out when you first sit down with this programming language and start to use it, we get to determine what that is and what it looks like and what's the philosophy behind it and how we're encouraging people to think, when they use this programming language and stuff. And so, of course, I care a lot about simplicity, and I care a lot about, well, there's two things. There's simplicity, and there's, are you afraid of the code that you're sitting on or not, right? So, like, there's something like, okay, like the way that libc seems to have gone at some point is that, first of all, almost nobody ever looks at the source, right? And secondly, even if they did, they're really afraid of it. And part of that is that things like GNU libc are super ugly and horrible for maybe sometimes for legitimate reasons, because they need to be portable to a lot of places, and that always messes you up a little bit. But in my opinion, they're way messier and uglier and scarier and harder to understand than they should be. And that helps encourage people to not understand what they're doing. And especially if you make it harder to understand, you're of course, helping people do that. And so that, if I want this code to be something that you just look at and maybe the philosophy is, okay, I'm going to push one more diversion onto the stack, or one more discursion, right? Which is, there's this idea in software that is mostly unquestioned, both in academia and industry, as far as I understand, which is that when you're making a library, you mostly want to make it general and handle whatever people are going to want to use it to do, right? And sometimes this gets taken to more of an extreme, sometimes it's less of an extreme, right? But the idea is that the best library is very general, right? Whether that means what data types it operates on, or whether you can put 1,000 or 20,000 digits in the output or whatever, right? And the problem comes that the bigger the envelope is of cases that you're trying to handle, the more code that you need, right? And the more code that you have, the harder it is for someone who's coming along to understand what the hell is going on. Because, if you needed to handle potentially 20,000 digits of output or 2 million digits of output, now you have like memory buffering and management of like your output floating point number. Whereas if you knew you could round it to 9 all the time, right, then you just have a 10 character long, thing. And that's added complexity that then increases the opacity of this code to everybody who comes along later, right? And again, encourages this being afraid of what you're sitting on, or maybe if afraid isn't the right word, just feeling like it's complicated stuff that you don't understand and you don't ever want to look at. So on the one hand, my impulse is to go back to, look, we're just printing out the number that's going to round when you parse it, right? And that's where we stop. of course, that's talking about printing, right? Where right now we're talking about scanning, and that's a little bit different too, because you're like, maybe you're scanning something that wasn't printed by you or anyone friendly to you, and maybe you need to scan a 20,000 digit thing. I don't know. But anyway, the point being, okay, let me pop that off for a second. So if then I want to have more of a trend toward having code be small and understandable than being absolutely general, right? Then the philosophy of things changes, right? Maybe a good library, like maybe a good core library. I don't know how this applies to printing and scanning floats because I don't know, but maybe a core library generally, like a hash table, for example, is not a hash table that tries to have maximum performance in all cases, but it's a hash table that fits a very specific use case, and that maybe gets slow if you throw something at it that's out of that use case. But if people want to modify it, well, maybe they switch to a different hash table, right? Or maybe if they need something slightly different out of it, they just copy the code and modify that code, and then they use it just like anything else. It's just their customized copy, right? And so I kind of want to try that a lot. Like, hey, it's totally okay to copy stuff and mess with it. Because in my opinion, and I don't know what Sean thinks about this, but I assume it's probably not that different from what I think about it. The whole idea of code reuse has had limited success throughout history, and the marketing about code reuse is a lot more I don't know what I'm trying to say. Like, the marketing presents it as not that hard, and if you just make good abstraction layers and put some comments or whatever, people will be able. If you just put it in objects and people can subclass your object, then people can reuse your code, and that's really not true, right? And so that's why the STB libraries don't look like what most people teach is reusable code, and yet they're more reusable than most other things out there, right? So like part of what I'm trying to do is go a different direction than what the dogma for decades has said is the direction to go. And so obviously that collides with this issue, right? Like, do I want to handle printing out 20,000 digits in the way that Sean's talking about people have decided, or do I want to do something else and then maybe just have a comment there saying, look, this is what you want almost all the time. If you actually want to print out a 30,000 digit number and have it conform to some very specific thing, use a different library, and that's that. So that's sort of what I think about all this, but I haven't thought about it specific to this issue, right?
So, excuse me. I think I totally understand your impulse there. Like, it's a reasonable impulse in terms of what you want from this particular
let me say
scenario
one more thing, right?
in your library. Go ahead.
So the obvious problem with what I just said is there's a different kind of simplicity, right? Which is just the user doesn't have to understand what they're using in order to get the result that they expect, right? And if you expect a 20-digit number because you just want your thing to look right or whatever, and you don't get that, then that actually is complexity and induced confusion and stuff, which is probably one reason why people veered toward the other way.
I think the main reason, I'm going to argue the main reason is different, but I don't actually know. But like, I think there's a reasonable impulse of like, the built-in stuff does the simple thing. If you want something crazy, use an external library. An external library can implement all of this complexity, but you don't, excuse me. Like, you could argue that like, well, the base code is going to get like stuck into everybody's executable. So like, maybe we don't want all that extra code. Like, you could like advance some argument for it, because the counter argument is sort of like, well, if this code is going to exist as an external library, why not just shove it into the base library? And you are also given other reasons, like, well, people should be able to look at it and understand it. So I think the thing to think of about what happened with the C string to float and float to string is that it was a historical arc. And I think the historical arc was driven primarily by portability, by the fact that different compilers, effectively different libraries, were producing different results for these things. And so I think that's sort of really the prime factor that drove it. Everyone's like, well, we got to standardize on a single thing. Let's standardize on the like, and we have this research that shows, hey, you can make this thing work. So let's standardize on the right thing,
Yeah.
which would be an argument that you could definitely not go down there that specific route, but just pick a standard. Like make sure your algorithm is actually like has some specifiability so that if somebody were re-implementing it, they can do the exact same thing. Which
Right.
could just be your code is open source and just use it. I mean,
Yeah. Well, so there's sort of two
like you're
issues here, right? There's a
you're in a
long-term
weird place.
issue. Oh, go ahead.
You're in a weird place because I don't know what your take is even on the idea of independent implementations.
I don't care about independent implementations right now. I think
But in
eventually,
the long term,
I mean, if something is successful enough for long enough, then that just happens, right? Like
yes.
I don't think I am able to say there shall never be another implementation, right? Um, that said, I think it would be pretty hard, right? It's like harder than another implementation of C by a lot. However, it's probably easier than another implementation of C++, and people do that, right? So
Mm-hmm.
is not impossible. And yeah, I totally understand what you're saying, where like, look, if I compile my code on Linux and I compile my code on Windows and it outputs a different file, I mean, never mind that the Windows file is going to have like different carriage return line feed or whatever. But aside from that, like, look, the numeric digits that it outputs are different. That's very annoying, right? And I remember having problems like that actually way back. I mean, they weren't exactly problems, but it was just like, I don't, I don't like what I'm seeing. So I kind of get that. On the other hand, right, it's my understanding vaguely that like I haven't looked at like Grisou 3 or 2 or whatever in a long time. But it's like thousands of lines of code, right?
Mm-hmm.
And something like reading a floating point number is going to get compiled into most people's programs. And so even though this compiler is pretty fast, the model is, also that we compile from source every time, at least for the foreseeable future. And so like adding a 5,000 line payload to everybody's compile every time just so that you can do something that nobody really wants to do doesn't seem like that good of an idea to me. Then, yeah, but I sort of have two different problems. One is the long-term problem about what's the right answer here in terms of the whole language and what we're presenting to people and all that. I have a shorter term problem, which is like, look, I just want to remove this dependency on libc and have my code run a lot faster because like A to F from Visual Studio seems very, very, very slow. I don't know why. I don't know why if it's doing the same standard thing that everybody else does now. It seems ridiculously slow. So yeah, so I sort of really want to solve the short-term problem, but not in a way that's incompatible with solving the long-term problem. But I don't also know the right answer to the long-term problem. And, when I'm designing a game or something, I kind of just let myself not know the right answer for a long time. And I just keep working in the space and just getting more experience thinking about it. And then eventually maybe come to some conclusion. So that would be my inclination here, is to like use this as data to inform the eventual approach. Now, the problem that I have is, okay, we've just sort of said, well, maybe this isn't a very good thing because whereas I don't really feel the need right now to handle like 1,000 mantissa digits, I mean, it is kind of reasonable that somebody might give it a string that has some extra digits, like a few or whatever, right? Or 10. And so that doesn't seem too good here.
Yeah.
But also, well, I'm gonna, whatever I plug in, I need a float 64 version as well. And so I guess this code base had that to, but I would have to, I don't know. I don't know. I kind of would like to just find something field tested that does the right thing, but isn't quite as picky about inputs as this. And the problem is, if what you're saying is fully accurate, there isn't really going to be anything kind of modern that does that except the full bananas, right?
Yeah, yeah, because everyone went that way. Yeah.
Which, and I don't really want to stop this. I have so many things to do. I don't want to stop the project and like figure out the float print algorithm that is short and reasonable, right? Or the float scan algorithm that's short and reasonable. Like, I'm sure I could think about this for a bit and do some modification of this that like doesn't, that handles extra digits and maybe just discards them after some point. I mean, I guess we could just discard them here, and instead of
You can
returning
discard
error
them
too
and-
long,
You discard them and remember that you had non-zero. What you do is you scan them and see if any of them are non-zero. And if so, then you know you had a non-zero value past the end of the mantissa, and that can affect your rounding.
yeah.
But it seems like you could do that. I don't know why that isn't right, but because
Yeah, maybe-
apparently it's hard. So
Yeah. Well, I mean, I can imagine why it's hard, like for exactly the reason you were saying. Like if you want correct rounding, it depends on the exact value of those digits, right? Because there will be some
Yep.
value
right.
that's
Yeah,
too
yeah, the
low and some
boundary.
value that's too high,
that's right. Yeah, yeah.
right? Now that said, I could imagine a crazy algorithm that goes forward, like you figure out how far you are from the rounding point, and then you sort of do a printf one digit at a time and compare it against what's in the rest of the string.
Yep.
You know what I mean?
I believe you will find that somebody has implemented it somewhere.
Yeah. I don't want to
other-
do that.
The other thing
Right
you could
now.
look at is what's the replacement standard library on Linux that's the small.
Oh,
in the
muscle
library.
libc. Yeah, we could look
Yeah.
at what they do.
You could look at their code. I think
Let's
you'll
see.
find it's like embedded directly into printf or something,
Oh, I'm sure.
or the
Right.
scanf.
The-
Yeah, like-
Sometimes people take things a little too far. Muscle libc
Yeah.
A to F. Okay, A to F.
Like, is
dot
A to
C.
F even a function?
Okay, it's
that
return
actually a-
stir to D. Okay, easy. We just port this. We're done. No. Okay, so stir to D. So I guess it casts it down. It just does. Like, is that correct to parse it?
No,
float
no.
64 and then
You
cast
double
it?
round. If you convert to double and then convert to float, you double round, and it's wrong can be wrong in the last bit.
Right.
So there you go. You're already
Awesome.
wrong.
Well, there's stir to F, which is different from A to F. So, like, A to F is just the function name that I know because I learned C in the 90s,
Oh, okay.
right?
Yeah, yeah.
In that way.
Yeah.
So maybe this means correct rounding and the other one is just specified to not really be accurate or something. I don't know. Okay, so stir to X is __ float scan. It goes from sort of a file, but it's like a buffer in memory that it points at the string. Oh my God, dude. I mean,
That
I
makes
guess.
sense because you need to implement fscanf to read from files, or fscanf has to read from files. So
I just would do that the other way around. Like, I wouldn't make my file abstraction be my string buffer exactly, but I guess that's the libc way. That's sort of like
Yeah.
libc. File in libc has always been like a local buffer and then
Yep.
file handle or whatever, right? It's just not what I would do. Okay, so __ float scan. Okay. Let's see how long it is. It's not short, but it's not crazy. And it supposedly handles 64 and 32. But it doesn't seem to have enough comments to really say what it does. What's the license too? Anyway, let me just see if like muscle libc float scan. Maybe someone's just talking about it on the internet. No. Nobody has anything to say about this. Here's where it was added. 2018. Well, so I don't know what the provenance of this code does, and of what it is, and I don't know what it does.
It's MIT license, by the way.
Oh, great. Good license. Okay, this is hex float. Okay, half of this file is hex floats, which I don't care about right now.
Good. Yep.
Well, no, not half the file, but 100 lines is hex floats.
Yeah, 300 lines isn't too bad, although... Oh, I see. No, the float scan starts down there. Okay.
Yeah, it's like...
So, yeah.
Okay, so let's just look at the high level here. So I guess you pass the precision of whether it's float or double. I mean, why you didn't just pass these in directly, I don't know, because this is an internal function. But okay. Well, I guess that's a little bit error prone to. Okay. So it also does long double, which I don't think I care about. Maybe I should. I don't know. What do you think about that, Sean?
Long double seems like a thing of the past since... Wait, I always forget. Does x64... I guess it does implement 8087 still. It's just nobody uses it by default, but...
Yeah.
Right, because the interesting long double case is the 80-bit long double, right? Like,
oh, yeah, nobody uses that. I remember being excited about that. And
but isn't that what that is? Like, isn't that what this is?
Yeah, I guess so. I for a minute I thought it meant 128, but then I'm like, no, wait, it must mean 80-bit. Yeah, I don't care about 80-bit floats. Okay, so that might make the code a little bit shorter as well. I don't know.
It doesn't look like it. It looks like it's just going to.
It's just going to set these values.
Yeah.
Okay. So it skips leading spaces. Okay, so right away you know it's actually used in production.
Yeah, this is all just a rapid deck float at the bottom is the real work. This is just catching detecting if it's hex or detecting if it's infinity and
What the hell is this? C or 32 is equal to the string infinity sub I. What the hell? Oh my God.
Yeah, that's the thing is that this is probably twice as much code written normally. Like,
yeah, but I'd rather write it
and
normally.
still without comments. So like,
yeah,
like put in the comments and it would be like 4 times as much code. Like,
so, like, yeah, if it's subtracting the 0 if it's less than 10. So that's like, is it between 0 and 9? This is it A to Z, right? Or A to Z. It's like doing a pre-scan. It's doing a pre-scan on the input.
I think that's to detect if it's...
And then it ungets the characters. Oh my God, guys. Like seriously, it's doing unget I times. I don't know about this code.
Well, I mean, some of this is to support the hex float stuff, I think. But
yeah, I mean that certainly
maybe.
Is right. The A to F.
Yeah, but
thing.
like just
but
the
like,
scan, because that scanning does a C minus A stuff, so it's obviously checking for the characters being in the A to Z range, which is Y. So
yeah,
I would look at deck float because that's the actual. You could replace all this wrapper stuff.
Yeah, I'm just worried when I see while I minus unget. I'm just like, you didn't even bother to do unget for n characters. That just bothers me, right? That's like,
Yeah, I mean,
that's a code quality red flag right there. But it may not have, okay. So,
like maybe this is the only place in the code that ever does it. I don't
yeah,
know.
maybe. But then put a comment saying, I know this is lame, but, all right.
I would just check the code quality of DeckFloat because I bet it's just as bad. So
Yeah. All right. Well, hey, it still doesn't use declare anywhere. It's the year 2020. I think you don't either, right? Or do
because
you?
I'm using a compiler from before the year 2000, so
Yeah.
I have to.
Well, I guess they want this to compile on that compiler. So, um, all right. Well, that makes code a little bit more annoying, but not that bad. So DeckFloat is 63 to 312, so it's not that long. Is it really that different from the code that I was just finishing porting? I don't actually know.
So does he have? Okay, see that
It
very
is
first
because
thing
it's,
you see that X Kmax at the
yeah,
top
how
of
big is
the
Kmax?
yeah because
128.
that's the big num equivalent thing. That's the that he's figured out he doesn't actually need infinite precision. He only needs at most. So yeah, it is implementing that.
128 U32s. That's not that bad. I mean, as big nums go, like,
Right.
it's not ever going to allocate RAM, right?
Right, and the point is, it's not like doing real big num math. It's just having to keep track of a mantissa that's that big.
Well, maybe we port this one, everybody. What?
Maybe we should figure out where this algorithm came from, and
Yeah,
you go
like,
back to the algorithm rather than this code. Or maybe you take this code and you first port all the shugets and shungets into pointer math or something, so it's more readable.
yeah. Well, so this is going to be really annoying to try to search for because apparently IBM has a format called DeckFloat that is a decimal encoded floating point number.
I think you want to like read the patch mailing list submission or something and see if there's an explanation of where it came
saw
from.
that. Like where was okay, so okay, add functions. Why does it say JSON colon? That makes me worry.
I think that was Jason was adding. Somebody was adding. Yeah.
Okay. Anyway,
So, somebody said, let's just use the musical code and not figure it out.
so well, authored by Lucas M. I don't know how GitHub works. Does that mean Lucas M did the patch request and then Julius Ferramer said okay and pushed the button? Is that what that means? I don't know where to search for.
It looks like the first check-in of floatscan.c was the thing, and it doesn't have enough info to figure out where it came from.
Maybe I can just search for the source code quoted, right? Like, let's pick something that.
I'll do other searches in parallel.
I'm going to search for this. Now, of course, Google is terrible for searching for code now.
Yeah, the fact that we lost code search ages ago, that was a total loss because code search actually worked.
I get one hit and it is the same file.
Yes, of course.
It's giving me images of airplanes though, because I picked a line that says DC less than 10, so it's showing me DC 10s. McDonnell Douglas DC 10. All right. Let me search for a human comment. Oh, well, it's from WebAssembly libc. So some JSON guy probably copied the file. WASI libc. Or did they copy it from Muscle? Oh, this isn't, wait. This is, okay, of course, because web people include a trillion dependencies, this is just the Muscle file included
Yeah.
in somebody else's code base. All right. RIP. Maybe the dude just wrote it and didn't tell anyone how it worked.
Yeah, it's possible.
I don't know. At this point, like, I just want to assign this to the intern and go, except we don't have an intern.
Yeah, but this is also not the code that you want to assign to the intern. I mean, you could assign
Yeah.
the intern the problem of find out where the code came from, but
I mean, I could just port this for kicks. It does look more serious than the one that was happening before, right? And it doesn't seem like it uses a lot of support functions from anywhere. Like, it just needs a few constants. Well, there's
Yep.
like copy sign and fmod. Wait, it calls fmod?
fmod
Okay.
L?
That's annoying.
No,
I
but
don't
it's
wanna-
fmod L. Maybe that's a special thing.
Oh,
Maybe that's some other manipulator.
All right, let me see.
Or maybe it's a long double. I don't know.
Fmod L.
I would have
Yeah,
just
it's
checked for an
100
fmod
lines.
L.c, but
Yeah, it's here.
oh, it's a real fmod, huh?
I mean, we do want fmod as well, eventually, right? So like that's actually useful. as
But
opposed to
it
being-
is on long doubles. That was so he's breaking out the long doubles to solve his. So you can't even implement it because if he
Yeah, I
requires
don't
long
support
doubles,
those. Yeah.
yeah, then you can't. If he was requiring long doubles for his algorithm, then
All right. Maybe we just
Which
give
makes-
up and
which-
keep using libc for now. I don't know. I don't know what
Yeah.
to do about this.
the
'Cause I don't-
long
I-
double thing makes sense. That like, oh, if he has it, he would use it because it is a right. Well, if you're trying to do doubles, well,
Yeah.
it even makes sense. He's trying to do long doubles, even, but even if you were only trying to do doubles, like Jeff's code uses 2 doubles to represent extra mantissa to try to do the rounding stuff better.
Yeah.
Even though he's not doing the infinite precision stuff. So even just doing that stuff, he uses 2 doubles. So you could see that if you had long doubles, you would use them. But yeah, it's too bad.
So
How
someone
does that
chat is-
even? Is this only for x86 or x64?
Yeah, well,
like
I
it
was going
seems
to ask
like
that. Like, does muscle not run?
nobody
on
else
ARM?
has long doubles. Yeah.
I don't know.
Well, in fact, the top of that float scan function has an error, pound error, unsupported long double representation. So
Oh yeah, I see that right now. Yeah. Okay. Well, that answers that for now. Someone is saying, could you just keep the current view port, but return a new status code if you detect the output could be off by 1 epsilon as a 10? Yeah, we could definitely do that. I was just hoping that there was something else to do. I do want to get rid of the libc dependency. Let me figure out. Okay, I'm going to figure out what my goal is for the rest of today. And I think the goal is we can go back to the port that I had there, that I was working on. We can finish that. And then hopefully the float 64 is not much different and we can either just copy it or, do something, make it parameterized in some way. And this will solve my short-term problem, which is just, I want to get rid of the libc dependency, and I want to have my code go faster. It doesn't solve the long-term problem of like, what's the philosophy here? But I don't think any of our beta users right now care,
Yep.
And so I can just put a giant comment. So I guess what I should do before continuing with this is spend a little bit of time just trying to see if there's something else that might be better, you know? Um, like, does anyone in chat have ideas of what I should look at that might be better? Someone was saying that Visual Studio has a new one that is amazing, but I think it was based on this actually.
It's also going to have some license that's not friendly, probably.
Yeah, of course, of course.
The other thing is I would probably do the 64-bit, the float 64-bit first, and
Yeah, well, and we
produce the
could even
32-bit
just
from that.
cast it, right? Like,
Yeah, exactly.
I don't care
'Cause-
about double rounding right now.
Yeah, exactly.
Let me.
All right, let me get off the talk because the
All right,
chat
man.
because I don't think
Good chat.
All right, thanks.
See it. Do it yourself. View is optimized for speed and doesn't even allow the what obvious stuff? I don't understand. I don't understand what you're saying. Look at implementations of standard from chars. I mean, as soon as you say std : I don't want to. And the problem is all of those are going to do what Sean was saying about being super bananas implementations. The Witness is 77% off, just saying. RimWorld is only 10% off. I guess people don't do super big discounts anymore. Like, look, most of these games are not heavily discounted. You bought The Witness on June 25 and got it for 40. Can you refund it and then buy it again immediately? I don't know if that works. Witness for you costs $2 because you probably live in a place with a very different currency conversion. Okay. I think Sean is correct that the right thing to do is do the double version of this. Which hopefully looks just like this so I don't have to waste my porting effort. Nobody is really suggesting any other options. Let me just look. Fast, simple, string to float. Of course, the number one hit is in JavaScript. Thank you, Internet. This is from Bananas JSON stuff. This is what we're looking at. This is someone doing weird stuff. Probably. Yeah, A to F, 19 times slower than a silly loop. Is this the same? Oh, this is the Grissu guy, right? I don't actually know. Maybe not. This is too new for that. Albert Chan. But it's complicated, so he doesn't understand it. That's not that long. I mean, there's probably support functions again, but let's see. Normalized 96 bits big float. Is that a software big float? I don't know where else you would get that. I don't like that. Arbitrary precision math library to break ties. Maybe we just punt in that case and just pick one. Yeah, so this is a I mean, it sure seems like the dude thought about this pretty hard. In your compiler, you use a trivial algorithm for converting string to float double if input has less than or even 11 characters and no explicit exponent. Yeah, I mean, definitely, and even in terms of like make the code understandable for people, if you could put the simple version in a file somewhere and say, hey man, this is the simple version, right? And there's this mess off in this corner over here. Oh, guys, fucking. So, is everyone still there? Is everyone still there? Hello, hello. So what just happened? I don't know what you saw. Maybe the screen went black. My new computer, because people keep messing with case designs, my new computer has the power button on top and it's flat and recessed. But like, if you just like lean back and put your foot on top of the case over like that, it's very easy to press the power button. And then Windows went into soft shutdown, but then it was like, oh, things are running, and I was able to cancel it. Yeah, it's not a good place for a power button. You need like one of those things like they have on the missile things on an aircraft, like a military aircraft, where you flip it up and then push the button. Maybe not put your foot on it? Come on, dude. Okay, what were we even saying? I was reading something from Sean, I think. Yeah. You don't know if there's a simple, robust, but slow algorithm out there. I don't know. I mean, I'm kind of tempted. Let's just see. Let's see how giant this code is. This guy sounds like he has thought about this a lot and knows what he's doing, but I don't know what that means. Like on the internet, who knows what that means? Sturdity light. What is light about? Is this just the main one? I mean, it's not that big. So we could just punt. Like, it's not that big and half of it is hex. So if there's more than 19 digits, if it's 28, we increment the exponent? Is nx the exponent? Like what? If it's 19, I don't know. I don't know what that does. Maybe he's got a comment about that. Sturdity light. There's no text file for that. Sturdity without big num library, close to 100% accurate, but not exactly. Close to halfway cases, assumed halfway. Okay. I mean, honestly, this sounds good to me. For now. It's a good point. Let's see how many of these files are needed. Okay. So Sturdity light. So these don't use anything. We do include two things. So we have all these mul functions. Let's click these open in another tab. D to A fast. Here. And right. MapM. The hell is MapM? That's in a whole, what? That's in a whole different place. Is that memory map? Why would you want to map memory? This is starting to scare me now. It's not even in the project. There's no MapM folder, guys. RIP. Let's see if the things that we need are here. No, because this just defines some functions. All these other things, all these muls and whatever, there's a zip file called mapm on the root. I missed that. Okay, let's see. MapM. All right. Let's see what's in this file. Wait, I've already downloaded 7. Wait, what? Open with. Seven zip. Like, why does it not register? It's freaking. All right. I had the option in the dropdown. Oh, there. Why is it there? That's stupid. Okay, don't ever do this. I hate that. All right. Okay, so it's fine. MapM. It's a lot of files. Okay, it's a math library though. Hyperbolic, sine, power. Did this guy just like write all this stuff? What is open? Why does this program suck so bad? Give me an open with, like everybody does. All right, this is garbage. We just have to do this. All right. Redocs. Why am I so confused looking at my menu? Open with. It's at the top. Notepad, buddy. MapM by Michael C. Ring. Freeware. Arbitrary precision math library. Math to any level of accuracy. Right, so it's a big num library. But then why are we including that? I thought the whole point of the light. But all that. Okay, so the APM is arbitrary precision math. Maybe he's just oh God. Okay. Okay. I mean, map MD to A. Let's just look at that. Includes common. Okay, this is where all these moles come from and stuff. So 96-bit multiply. Okay. Fast BF96. Do we need that? Okay. So this is an arbitrary precision math library, but if you define this multiply only once, that doesn't sound good. I would not use that. Okay. But then you have to do all this. It's still not that bad. Okay, so these don't seem that bad. What the hell? Bit 96. What? ePrint. Why is that called bit 96? Is it printing a 96-bit number? Okay, so it's printing this and then the number. I kind of want to try it. I don't know. We need count leading zeros, which we don't have an intrinsic for, but we can just write that again. Wait, is that long count leading zeros? Hold on. What's M? Oh, that's... Where's M? Yeah, it's 64. So long means 64 here. The big table is used in a macro. Fast BF96. Yeah, that seems like something that... Right, it's used in mol96. Like, why is the define and the table name the same thing? Oh, no. That's only... Okay, wait. So if you define fast BF96, you get this. All right, so mol96 is... Mol96 requires fast BF96. I guess this is only a do while for archaic C reasons because it's a while zero. So, um, so we would need a lot of these things. Okay, it seems like we need this whole file, most of which is these numbers. It's like the numbers from Lost, but more. It's a pretty big airplane they were all on. The actual part of the file fits on one page, aside from that table. "73 divisions doesn't seem that bad." I don't think it's 73 divisions. It's, where am I? Hold on, where are we at? I forget where that code is now. Dude, where is the thing? Right, wait. Okay, it's back. If we don't fast BF96, we had some alternative code. Where is that? My brain doesn't remember anything. Oh, it was in Sturdy Light, right? So we were like, if we don't have fast BF96 here. So this is like for every, I guess I is the exponent or something, or it's the middle 32 bits of the mantissa. Of what? What is this? What is M? It's an input number. Anyway, so it's a middle 32 bits. I mean, I guess this could be a long loop, actually. I don't know, man. So the reason why I was worried about this, so fast BF96, it says some stuff in here, and maybe again I don't care for current purposes. But it seems to imply that you don't handle the full range, right? So C sub 0, what is C the big num? So is this supposed to be, is C sub 0 supposed to be the big endian part of the big num? Of a 96-bit, like I guess this is 32 bits, right? So it's a 3-digit thing. It's a 32-bit numbers. I guess that's okay. You think that comment is just proving the code is safe? I see. Oh, right, because you can't overflow. Okay. I get it. This is why I wish people would explain things better in comments. There's an art to explaining things so that other people will actually understand them. Okay. I mean, I kind of want to do this, but it's also going to suck. I don't know if we'll get it done tonight. So is C, like, is that just an array? Like, I don't even know. I guess that's a global. Oh, wait, it's right there. FastBF. Okay, that. Oh, never mind. Right, that's the table. I'm blind. That's the table. Oh my God. 1E minus 351 to 1E 339. Okay, so this is 700 different 96-bit numbers is what we're looking at. Yeah, 691 of them. OXFFBC constant is the max value from the table. Let's see. FFBBC. Yes. Okay. So I guess these are like big endian. So these are like 1E whatever times something or modded by something. Like, I don't get what the digits are. Oh, it's just maybe that number, right? This is 1E whatever in base 10, and this is the base 2 representation to 96 bits of precision rounded, probably, right? Yeah, that's what Sean also just said. You would have just said fuck it 2 hours ago. But this is, look, you don't want to be a Stack Overflow programmer. You know what I'm saying? And honestly, the best parts of game programming is when you understand things that are interesting, right? And that's kind of, it's Sunday. I mean, God only knows there's many other things I should be working on today. But, it's like I'm just learning a little bit about how people solve these problems and what that looks like. And that's the good part of programming, because if you take that away, then programming is just trying to figure out why Visual Studio takes 6 hours to compile your program, right? So that's kind of what we're doing here. Like if I just wanted to Stack Overflow program, we would be doing something else, right? Let's see. So this FastBF 96, we could just call this C, right? And local it, unless it needs to be referred to externally. And none of these have to be macros. They could all just be inline functions. I mean, I guess that would make it slow in debug build, but that's what I would prefer for debugability in the short term. Let's just do this. And then, like, no matter what, we should be able to finish this. Yeah, since this is N2, N1, N0, I guess that's the format. It's like high bits, middle bits, low bits. And then I don't know what the hell all this stuff is. Oh. High bits, middle bits, low bits of A, high, middle, low of B. And then BX is binary base 2 exponent of these digits, right? So it's just like, yeah, it's just a 96-bit soft floating point number. So we could just test this. We can put this in. We can make some floating point numbers and try them out. We could even start with things that are 0 in the low bits, right? So that we can verify that they have the same result, for like 64-bit floats, for example. What's the license on this? It was public domain, right? Didn't it say that? MapM. I thought, docs. README. Software is freeware. So we need to copyright notice. I mean, I would just copy this whole file into the module, even though we're not going to use most of the code. Or no, maybe I'd just copy, I don't know. Let's read this though. Okay, yeah, this actually isn't relevant because we're not doing big nums right now. We're not doing big nums. We're just doing the 96-bit. Okay, I kind of like this. You know what? We'll just port this code and try it out. Not this code, not that code. We'll port this code, this MapM stuff. We'll try it out and just have fun with it. And it's pretty easy. It's not that much, right? We've got our fine Starbucks meal. Was the Ryu code not any faster? No, it's not that it wasn't fast or that it was bananas. It's that it had input size limitations that we don't want. It's not that it was too complicated, it's that it had input size limitations. And, well, and that meant that I was going to have to at least co-author it further to get around those limitations, and I didn't want to do that. Okay. We're going to set that code aside that we ported halfway. We're not going to delete it because we might want it later. Emacs closed when I half rebooted my computer, so good on that. Okay, so we have set this file aside. We're going to grab this. Oh boy. Okay, so I don't think I do array literals like this right now. Whoa, that was interesting. Right there. Oh, is that this one? That's where we go to 1E0, right? Anyway. Our array literals kind of suck right now. Our struct literals definitely suck. I'm just going to make this a 1D array. Whoops. Which honestly is probably better anyway. Okay. Did I mess that up? Let's start simple. Oh, we need a shell. No, that's the wrong thing. Let's get the compiler into the buffer. What did I do wrong? How did I mess up that soon? What I did was I forgot to put the type in our not that good array literal here. I think we're going to get rid of that, but comma expected. Oh, yeah. Whoops. Not query replace. Replace. All right. We use commas every day. Undeclared. I messed up simple string. Oh, because I pasted those things over. I mean, we're going to get rid of this eventually, probably, right? But A to F. What a bunch of crap. What a bunch of crap. Why did you define that? Okay, great. We've messed up, or we fixed our mess up there. Okay, so we're going to go main is going to do nothing. So we have a compiling program. Now let's start looking at these things. Okay, mol96. Okay. If these are actually used, none of these are used in this file. Okay, so unless our main code uses them later, we don't need them, actually. Okay. We're going to leave that comment there, even though it doesn't exactly mean what we thought. Okay, mol96. I don't know what bexp is. I guess it's an int, right? Which means it's signed. I plus 351. So the 351 is, whoops. We didn't get the comment on fastbf96 for whatever reason. Just this little one, okay. That's important. So that just means we're starting at 0 when we go plus 351. Times 3. 96. Base is that. So instead of getting a pointer, I'm just going to make an index, right? And we're going to go x0 is so we're making a 64-bit number from the 32-bit number and then multiplying, right? We're component-wise multiplying. I get, you know, if you draw this out, it's probably just doing the very basic math thing, right? Of a plus b plus c times d plus e plus f, right? Except it's n2 times 2 to the 64 plus n1 times 2 to the 32 plus n0 times whatever. Wait, did I delete? Oh, this is multiplying by an element in the table. I see. I gotcha. We're going to have to comment all this later. I was like, where's the second argument? Oh, the second argument is the thing in the table. Right. Let's just say right? This is going to be a lot more readable. Okay. And then in fact, hold on. Let's back this out for a second. Right, so this x0, x1, x2 was just like that, right? Get rid of that. So we assign these. And we can just lackadaisically cast these up. We don't need to write it. So we can just do that. Now, x0 is c0 times n0. x1 is c0 times n1. x2 is c0 times n2. This is going to be a lot more readable, honestly. Okay. X0, they're casting to unsigned, but it is unsigned. Like, X0 was unsigned U32, right. They're doing that to truncate the number. So we tend to do that a little clearly here. We go cast trunc U32, right? So you say explicitly what you're doing. And then this is just C1 times N1, right? Let's just do this. C2 times N2, C1 times N2. Right? So it's just doing a cross-term multiply, right? Am I making stupid mistakes? Anyone? Okay, we don't know what normalize is. It's copying the x's back into the n's. And shifting, like, where's that defined? Probably in common. I hope that's not 10 million lines. Like, why did it just open Visual Studio now? Okay. I don't see normalize. It's probably in whatever's included by mapmclz. No, because that's probably... Oh, it is defined in there. It's just later in the file. Right. Duh. It's right there. What does that do? If the high bit is set in X, then that was a really big multiply. Okay, so we're basically cutting off the low digits and rounding. Okay, we're going to say we're going to be all functional about it rather than stuffing into pointers. Okay. So you know, all this code strikes me as really weird. Like, not this code specifically. Oh yeah, also return exponent. Good point. So Sean, doesn't a lot of code of this kind strike you as suffering from just not being able to do like double-sized multiply like you have on every CPU, or like add with carry and stuff like that? Like, they always do all this slow stuff and then hope that the compiler replaces it with add with carry, right? And it probably doesn't. Like, this is just, I don't know. Like, if you were to write the assembly for a lot of this, it would be shorter in some sense, is I guess what I'm saying. It's intermixing 32 and 64-bit operations. You don't even have types because they're macros. It is a little weird, but I mean, I guess like looking at this normalized, for example, it's, you know, like this is hey, we're right shifting it, and then we're adding from the neighbor, right? From the neighbor's high bit, which that's an add with carry into this sort of. It's just, would you have still had the carry bit around? I don't know. Except it's not, I guess it's not an add though, because it's ORing it into the low bit. Never mind. I have no idea what's going on. I have no idea what's going on. X0 and X1 are already only 32-bit. Really? No, that can't be right, because of this, if X1 was already only 32-bit, I think they're all 64. If X1 was only 32, this would give you 1 or 0. But then you're ORing X. Oh, you're getting 1 or 0, right? This is the low bit. And this is all the high bits except for that, which is why we're shifting. I have no idea what's going on here, guys. That's clear. So let's go back and look at the top. These were all some 32-bit number, right? So C0, 1, and 2 are 32-bit numbers in a 64-bit type, right? So the top 32 bits of all of these are 0. We go C0 times N0, C0 times N1, C0 times N2. That could be 64 bits, but I guess this... Oh. Right. So this is... No, I don't know, because then it adds another multiply in there. I thought it was all three numbers that all have 64 bits worth of bits potentially. Usually not. Usually a lot of the high bits will be 0, but a lot of them are maybe set, and then you're shifting them to get rid of precision you don't need. Except that doesn't make sense because I don't know, man. Yeah. Yeah, I agree. I agree. Input and output are 32 bits, and it's a 96-bit number. That all makes sense to me. I just don't get what's happening. I don't understand the middle part. What's 108.853? I have no idea. But it's probably something, like this is their exponent, and the exponent probably has a bias in it, and that bias may not correspond to the IEEE bias, right? Maybe B stands for biased and not binary, right? Okay. I think the intermediate number is x2 times 2 to the 64 plus x1 times 2 to the 32 plus x0. I mean, this would be a great thing to put in the comments, right? So they're overlapping. Right, that would make sense. If they are not overlapping, then shifting doesn't make any sense because you'd be destroying precision and leaving zeros at the top, you know? So they kind of have to be overlapping, I think. So if we get this to compile, then we have something that compiles again. Okay. We'll leave that for a second. Yeah. See, like these, it's a little bit interesting. So this says if we're using all the bits, then we know there's no zeros anywhere in here, I guess, right? So we say the top 32, then the next 32, which is the bottom 32 of the top. So this is like cast U32. Wait. These are 64-bit. Why did I put 32? This is 64. 64. 64. Right. So this just says if we're using all the bits, then just return the top bits in 3 numbers, and then like that. Otherwise, the N0 is X1, I guess is this, right? Because it's assigning. Unless the inputs to this are also actually 64-bit despite having 32 bits of precision. Do you see what my confusion is? I hope not. Inputs are 64-bit, all of them? Or just the X's? (108,853) is 1 left shift 15 times log 10 over log 2. Just X's. Yeah, okay. That makes sense to me. Okay. Okay, otherwise, return X2 right shift 31 so we know that the top bit is 0. Right? And 1 is some stuff, and 0, well, I was going to try to skip it, but yeah. So X1 whoops. Do I need this truncate? I think so. So this is, oh, this is just the low bit. We could also mask it instead of casting it. Let me just, okay, so this is this. I'll put parens, I don't think I need these parens, but it's that. We're truncating x1. We're right shifting that by 31. We are ORing it with x2 left shifted by 1, which is ORing it with the low bits of x2. Right? I don't know if I screwed that up. That's just, okay. Let's assign this. Oh, wait. It's a little confusing because we use these commas like syntactically. Yeah, this is going to make more sense. Okay. R0 is right shifted by 31. Our parens are not even balanced. That's like not. I don't think I need these. I'm actually not sure, but I'm pretty sure our cast is very tightly bound. Okay. Okay. I mean, I guess. So this, I guess I'd rather write as a constant. Maybe. Maybe not. All right, how much did we mess up now? That's a weird, I need to think about that, but okay. X2 right shift 32. Oh yeah, because we didn't. I mean, let me just write it out. It's just gonna be easier. Okay. Hey, we have a program that doesn't do anything. Okay. Let's do some of these. So these are all made to overwrite things in place, I guess. So when we expand them, they're going to be a little bigger. Like you almost just want to put this into a struct, but like that could have speed effects, probably does. I don't know. It would read much more nicely if it were in a struct. It might not actually be slower because we don't copy structs. You know what? I kind of want to do it. Except I don't know what the usage code is going to look like if we do that. If we'd end up packing structs in an annoying way that we hope it gets optimized out. Okay. Okay. I mean, in one sense, this is really a lot longer than this, but in the other sense, this is a macro and we hate C++ macros or C macros. So, you know, it's just going to be a little bigger. That's all. I'd much rather be able to step through this reasonably and like look at values and all that. And again, this would get a lot shorter if this was just a type. So I don't know. I don't know what to think about this. So this is the representation of 1E60 in 96 bits with the biased exponent of something or other. Okay. Mole 32. I hope we don't use that. I don't know where that table is. All right. It's probably not that big. Maybe it's just in this file. At least this makes sense to me. Like reading through this code, I'm like, okay, I get it. But if this was a struct, it'd be very easy. It would just be n and r and then return mol32 of n with, well, you wouldn't want to have to pack these into a struct, so you would be like, Okay. But I feel like, so right now when I look at this, there's just a lot of numbers and my brain just glazes over. But it's probably a lot easier to debug. There's just a lot of stuff on the screen right now. Like this is more compact than this. And what part of that is no spaces, but like, you know, we're writing out return values where he's not, and return state. That's the main difference, is this and this. And yeah, I don't know. So this is weird. Is this mol96? I think it's called a mol96. Those are all 32-bit values on the right. But this is 64. Oh, because these were ULL'd, right. So these are actually 64, even though they're not. So see, this is the weird thing about the macros. They were using the ULL to force this be the right size, which is a little bit invisible and dangerous. You don't want to do that. Like, it's just much better. Like, look, dude, just define the function, right? Right, so this is much less mysterious. And then this uses no T2. And then this, I don't know why it's not called T0 there. I don't know why it's called K. All right. I do really kind of want to make it a struct. Because then the underscore functions, we'll get it working first. Make a struct for n2, n1, n0, bx. It would make all this a lot more readable. Also, it would be a good test of the compiler to ensure that it doesn't make the code any slower, which it may right now. But it's good to know that, because if it doesn't make the code slower, I would much rather have the one struct version than the 4 parameter version everywhere. Because it's bananas. Whoops. I could also make normalize just be a macro. I don't know. Okay. Like, maybe these should be U32s and we just cast it. Because these aren't supposed to have high bit set, I don't think. Although maybe they can. Maybe they can. I don't know. A comment would have been nice, bro. Comment would have been nice, bro. Nice, bro. Nice, bro. Okay, we're gonna have to do some things here. So, okay, so he's actually casting K. Like, what? Let's do it. Even though, like, it's just very easy for me to screw up something that's subtle and undocumented, right? Like, oh, these things do need to be 64, but these things don't. These things have to be 32 because blah, blah, blah. All right. Okay, now this is fine. I don't know, everybody. Is this a disaster? Maybe. Semicolon. We did not use semicolons every day. Up here. See it. Oh, can't put a do there. Mr. Do. I forgot to declare my returns on mul 96. No TBX. We didn't declare that right. Oh, because I just copied the line. This is KBX. Screwed that up. Screwed that up. Screwed. It's what happens when you make a mistake and then you just copy it over and over and you don't ever notice. Right. So we don't have fast F32. that was not in the file. Fast F32. It's in mapm D to A. Mapm D to A dot H. It's like a lot of this. Wait. No, that's the usage of it. That's the file that we're in. Wait, what? No, it's just it's a copy of the. Am I going crazy? Is this? Is that not the file that we were in? It is. Did I just lose it? Did I just accidentally? Okay. Wait, this is if it's not defined. So we don't need fast F32, right? We don't need our FAT32 file system, which means we don't need mul32. This is confusing. There's underscore mul32, which means multiply by a 32-bit argument on the right side. But this mul underscore 32 is a weak sauce that we don't want, is my theory. All right. So how do we test this? We can say something like, so these are integers, right? These are 96-bit integers with an exponent. I guess there's no bias on the exponent, actually, because it can be negative. We're 800 lines, which makes me sad, but you know what? Most of it is this table. Okay, let's pick two 64-bit numbers. A right, and then B I'm going to make it not overflow, right? So I think that won't overflow. And then we got to encode it in the specialties. All right. '48 BC, 962F, 395F, 8190. Okay. So, well, let's say n2 is this, right? N1 is this. No. N1 and 0. N2 is 0. And then nx is 0, right? And what's the I? This I is like some overall where we are in exponent space. You know what I'm saying? Oh, no, no. Sorry. I is the table index of what we're multiplying by, right? So we don't want to use this. And we want to use this underscore mul, not mul underscore 96. We want to use mul underscore 96, right? Okay. I mean, we're not really testing a lot of the code by doing this, but oh. Okay. And then that's 0. And we're going to say mul 96 great. And then what's that going to do? Not what I thought. So am I using it wrong or is it broken? Like, what are the odds that we actually would get 0? They're very low. Is 0 a valid exponent? I think so. I honestly have no idea. I mean, we should have numbers here, right? That doesn't seem good to me. So that's before the exponents come into play. So x0 is the only one that's non-zero for some reason. x1 is this right shifted 32, which is going to be 0 because this doesn't have that many bits for some reason. Which I kind of feel like it should. N0 is big, but T2 is not. T2 is 0. So that gets knocked out. T1 times N1. I should have just called these T. Let's do that to be less confused. T1 times N1 should be 3 times this. That looks like about the number that we get. And then T0 times N2. Yeah, so this is just the middle terms. X1 is X0, right shift 32, which is 0. Plus T2 times N1, T2 is 0. Plus T1 times N2, N2 is 0. Okay, I am getting the feeling that these numbers are not allowed to have zeros at the top. Just like the numbers in this table, they are supposed to be left shifted as much as necessary. Yeah, so Sean just said that in chat while I was figuring this out. That annoys me because now I have to like do stuff. Now I have to like do stuff. All right, so this is 48. So you put minus 48 there. Oh, wait, can I just call normalize? Is that what normalize does? No. I don't want to have to deal with this. All right. I'm hungry again. I just ate. We're getting a snack. We're getting some more pita chips, cinnamon sugar. It's good action. Okay. Like, I could manually normalize this. So I just wanted to leave this here as a record of what I'm trying to do. And then I do this so that I don't just mess it up and then make a mistake. If I mess up the original numbers and then make a mistake, and I'll never find myself, right? So bam, 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 right? Except, what is this relative to? Is this like relative to the top of the number or the bottom? I don't know. It actually doesn't matter for the significant digits because this never combines into those. Wow. Wait, what was I even doing? This is this anyway. Okay. And then we say right? Now we have the same problem. I should have thought about this. We have the same problem because that math is symmetric, and now our bottom digits are 0 instead of the top. Normalize, you never use any of the n variables, so you could simply, yeah, well, I don't know how to test this now. I honestly have no idea what's a good way to test this. Try the C version. Try the C version on what? On the whole thing? We don't have the whole thing yet. Try the C version on random numbers, maybe. I just don't want to compile a C program, honestly. Build 2 floats. Extract the mantises to the high bits of 96-bit. Compare to double multiply. I don't see how that's going to help because this code looks like if anything is 0, then it hoses me. So like, if I don't fill the 96 bits, then I'm hosed, right? That's what I kind of don't understand. The bottom bits can definitely be 0, then why are we failing here? If the bottom bits could be 0, then this should work, right? Okay, well my t's are all 0, which would explain why I'm getting 0. What? What did I do wrong? Oh. Dummy. I am dumb. All right. I have a feeling that the top bit is supposed to be like 1.0 or something, or implicit 1. So this is maybe supposed to be plus 48. And this is maybe supposed to be 20. Right? Well, that is not remotely the number that went in. Maybe the top bit has to be 1. No, because the top of normalized checks if the top bit is 1 and does 2 different things, right? Right? If the top bit is 1, do this, otherwise do that. So, you know. Yeah, I notice it isn't written to find the top bit and shift. I realize that. I'm just saying it's not a requirement that it be 1 if it checks that it's 1 and does different things. Maybe output does. What do I do? I'm a little bit tired now because I've been streaming for almost 8 hours today. But I kind of want to get this done at least. Like, I don't know if I'm doing something wrong calling this, which is likely, or if I made a bug in the conversion, which is also likely. Right? Both of these things are likely. Is this single or double? It is 96-bit precision. That is the point. It's these weirdo 96-bit numbers. Why are you spamming the chat with converting float to... Stop it. Okay. It's from the PDF for this. We're not looking at float manipulation right now. We are looking at 96-bit fixed point number manipulations. This has nothing to do right now. This particular code is not at all about float to string, string to float, float to int, or int to float. Zilch. It is not that. Not that. This is just fixed point math. Well, I mean, it's sort of float math because there's these exponents. Okay. So I don't know. So, I mean, we could start looking at this kind of a thing. Like this is 1e25, right? In decimal. 10 to the 25. This is 10 to the 60. Right? Which is a little bit less than 2 to the 200, right? Let's check that. Let's check our fundamental assumptions. So, how 10 to the 60 in base 2. Will it do it? Oh, base 16 maybe. Okay. This base 16 is maybe the answer, except there's an implicit 1 bit at the top. That's the other thing I was forgetting about, is maybe there is an implicit 1 bit. Have I tried multiplying by exponent of 0? Not, well, I did that first, but then the top bits were 0, right? So if I multiply this by 2, nope, that's not what I wanted. Okay, okay, so that does correspond. So this says 200, right? This is 199. So we're at least not wrong about what this number is. It's just, how do I get... Oh, wait a minute. Oh, there we go. Was I blind? Was that there the whole time? Okay. Yeah, so this is just 10 to the 60 in base 16, all right? This, yeah. Okay, makes sense. So this is the log base 2, right, of the number, and this is the significant digits of the number. With, I guess, this is fixed point so that the decimal point is on the left, right? Which is why this is 200 instead of 199. So this is a number less than 1. Right, great. So we should be able to convert things to that, right? So let me just... We could just multiply some doubles. Okay, let's change our test. Instead of doing this weird integer thing, we're going to say just pick a random power of 10. Right. I don't know. Okay. Inf, right. Because it's just too darn big. Okay. We didn't have that many significant figures left over. Let's bring these close. That wasn't really better. Oh, it's this part. It's this 11111 that's messing it up. No, it's not. Wait. The 11111 rounded off. It was thrown away. Oh, I guess that's like all the precision that we have here. Is that right? I guess. I don't remember how many decimal digits it is. Okay, let's just... Okay, that's a number. It's pretty big. It's more than 64 bits, right? No. It's not. You have to, okay, you have to use more than the mantissa bits, right? It's 2 to the 53. Okay, right. So we want to do something like this, and we're just like, look, the double doesn't have enough precision. So what we want to do is then do the fixed point multiply that's equivalent. And then we want to see this, but with more significant figures. That's my plan. Why 96-bit? Because that's enough to do some things, apparently. Okay. So what I want to know is POW 822 in base 16. That's a very round number. Makes sense. It's power of 8. How do I... This is annoying because none of it is like really exactly what I want. Actually, if we take the log base 2 of this, it's going to be an integer. But then I think I want like all F's in chat. Or not, or, okay, let's just say, so log 2 of 8 to the 22 is going to be 66, right? Am I not stupid? 66. So N2 N1 is 0, N0 is 0. The exponent is 65. Is that correct? I don't freaking know. Okay. Um, $67? 67. If it was 1 in the high bit, that would be 66. We have right shifted the mantissa. So we need to add what? I think it's 67. Okay. So now 7 to the 17. Okay, log 2 of that is 47. So it's going to be 48. And then in base 16. How do I copy this? Is that like not a thing? D3938 3266E. Okay. So like that's like the numbers that we want, apparently. Oh wait, except this is too big, right? Okay. D393 8326 6E87. All right. And so we multiply those. Let's multiply those and print it out. And then we have to like somehow compare these. All right. So this is this. What did we do for result? Okay, no, we didn't want that. So we're going to 210 and Rx whoops. Okay, so we've got some digits and then a 114. Let's just say do we even have a log 2 of an int? Blah. Actually, we can cast that to int. What? That's an integer log 2. Why? What? Why is this here? That's what happens when you let people just put code in. Why is there an integer log 2? Ugh, okay. Are T even inputs to mol96, or were those outputs in the original code? They were inputs, right? See, these are factors. Underscore mol96. So not, see, Sean, you might be thinking of mol underscore 96 and not underscore mol96, which is obviously a very different function, all right? Let's get this straight. Nobody should ever confuse mol underscore 96 with underscore mol 96. Anyway. Wait. Was my log 2? Let's get rid of that. That was, we might bring that back later, but so this is the decimal form. That's not really going to work. You have to, okay. So our exp is what? Is 114. Does that sound right? 10 to the 50, 40 is about 2 to the 1. Yeah, that's about right. Okay. So if we say I mean, that's going to overflow. Yeah. Wait, why did that make 0 though? It shouldn't have made 0. That's 50. 1 left shift 50. Oh. Why is 1... What? How are we multiplying and getting 0? I mean, obviously it's an overflow, clearly, but how are we overflowing to exactly 0? That seems very suspicious. Is that even possible? I guess it is. All right, well, we're overflowing to 0 if these both have a lot of bits in the bottom that are 0. Right. The one that uses this mapm. Yeah, I still have that up here somewhere. It's Sturda D Light from this dude, HN001 on GitHub. I mean, maybe I should just forge ahead and do something here. Like, look at how this uses it. Oh, guys, I deleted that bias variable and he uses this down here. So maybe these exponents are supposed to be biased, but maybe it doesn't matter. I don't know where I'm at right now. All right, it's a good point. So this is mul underscore 96 right up here, right? So that multiplies by some entry from the table. Oh, do we not even need the other moles? Have I been... So we need these, and these use underscore mul 96. Oh, wait, no, that's else. Wait, we didn't need any of this. Do we literally only need mul underscore 96 by the table? Have I been that dumb? I just remembered seeing these, and I was like, oh, well, we better port those. But those are... If we really only need this... That uses normalize. That doesn't... Oh my God, guys. F. Oh, we do use it. Oh no, that's just this. Okay. So I guess, so this is 1E0, which is actually 1 in the high bit here. This is 10, right? 1 times 10 to the 1. This is 100. So how do we know, like, none of these constants have exponents on them, right? Like, how do you know what the exponent is? Wait, this isn't... Okay, hold on. 1, 10. That's not 100. Okay, this is even... Wait, weirder. There's no exponent table, so you have no idea what's going on here. Yeah. It's implicit in some way. Like this is 1, but like shifted right 1, right? This is 10, but shifted right 2. This could be 100 shifted right 3, 1,000 shifted right 4, right? 10,000 shifted right 5. Well, shifted right if you were imagining it to be the left of the x, right? If the x was the decimal point. But this isn't 10 shifted right 2, it's 10 shifted right 3? Seriously, look at the multiply by 108853. Dude. Exponent gets converted from base 10 to base 2 by multiply. But that doesn't tell you how, like, what we're asking is what's going on with just this table. Okay, so I is the table index. Wait, no, that's not the table index. It's the power of 10. We get the table index by adding the 351 multiplying by 3. Okay, so I is the power of 10. Then why do we need bx? Oh, this is the power of 10 that we are multiplying by. Bx is part of this number, right? So this is, okay, so maybe b is binary, base 2, right? This is base 10. Okay, so this is not stored in the table. This is not stored in the table. It's just computed. And I guess this is all the precision that you need to do that. I kind of get it. There's a formula for the exponent, and then a table of mantisses has been constructed to match. Right. That does make sense to me. Yeah. Let's see if we actually, okay, if this is all that we actually need. This is short enough to believe it probably doesn't have stupid mistakes, or not that many, and we can figure them out. Table is fine. So like maybe the actual step would be to go to the actual float thing. So this is obviously a more interior routine because this is the top 64. This is the bottom 32. It's a weird thing. Bx bit already has for that. And then power of 10, which I guess you just increment 1 to I for every digit or something, right? Or I guess, I mean, it depends on what order you're generating your string in, right? And then is it negative? Okay, so stir to D fast. We could start on this. Like some of this is obviously very easy. We're not doing hex float. Some of this I don't really know what is going on, but okay. So we add one for, this is like a pre-pass. I don't love that, but okay. I mean, this is surprisingly short. seriously was what you needed to get you to pay attention. Yeah, no, I mean that actually was helpful. Okay. Let's just start doing this and see what happens. And then if it doesn't work, which is likely, we have something we could just like step through and see what makes sense, which is sometimes helpful, right? I don't think we're going to get there tonight, honestly, with as long as this is taken. All right, sturdy D fast. End pointer we don't need. And then, right, is that? Yeah, we just do that. Okay. Okay. All right. I don't like this comma thing. Let's do an index again. OX800. So that's going to be a, you know, go get ORed with the exponent field at the top of the thing. Just like the other thing that we ported halfway. Wait. All right. Let's just do this to be all parallel. I don't know. Okay, so skip leading zeros. See, this doesn't seem to be checking against the end of the string. Like, what? Like, what if I just pass you a string with zeros? I guess it's zero terminated. So you would end at the terminating zero? Yeah. All right. While n is... and... okay, skip leading zeros. Star P or 32. Oh, this is converting to lowercase. Bro. I don't think I've ever seen that before, or I haven't seen it in long enough that I forgot. That is some ghetto lowercase conversion. Okay, we should be returning float 64, right? And probably a status code. We're just gonna return instead of doing the if check. Actually, we don't actually have to say that. Okay. We're not gonna check for X here. This is not a thing that we're doing. Maybe we should. Everybody seems to do hex float. I don't know, man. All right. So yeah. Right? Yeah. I feel like I'm really tired. So it is likely my propensity to make mistakes has gone way up at this point, which is kind of bad news bears. You've never seen it before. You're copying it into your compiler right now. It's very obvious in hindsight, right? You know, but that's, you know, the C to upper and to lower macros, or to lower, I guess, doesn't usually work that way, because if it's not an alphabetical character, it doesn't want to return you the wrong answer. But this doesn't care, because if it's not an alphabetical character, it won't match anyway. So it's fine, right? Hex floats are better for serialization. Oh, I agree. Like, but we just write out the IEEE number as an integer, right? Like, I don't think I would do anything besides that for hex floats. Yeah. Okay. Okay, so we didn't make an isDigit macro. Maybe we should at some point. Just before decimal point. Okay. So we're counting digits. If digits is greater than or equal to 19, if it's 28 exactly, we add 1. If it's 19 exactly, M right shift 32. All right. So M keeps the... Wait, bot is the high bits of M and M keeps its low bits? Okay. Okay. How much of my level load time is Sturda-D? So in the shipping game, none, right? Right now, though, we load these giant character animations that are text files, and there is a substantial hitch every time we do it. And I just want to make the hitch a lot smaller and, you know, sort of solve this problem for people a little bit. But yeah, I don't know. Okay, all digits is LZ plus digits. Those are different types, aren't they? LZ is S30. Oh, no, they're not. Okay. Why did I say? I keep seeing P. Digits after decimal point. Oh my God, dude. If plus plus P comma not. Are you kidding me? Just put the plus plus P outside of the if. What is going on? This guy is silly. If plus plus P comma not digits. Does this do anything subtle that I should know about? Like, what is that, dude? Who does that? This guy definitely learned C in the 1970s. All right. Okay. Oh. Wait, we do more LZs? All right. Okay, now I'm really confused. Okay, we got to go back and look at this. If, okay, this is just that. Okay. So, right, this if is just that. And then we do the same thing. All this 1928 stuff. It's like literally the same code. It's exactly the same loop. Which, this looks a lot like the other code, honestly. I mean, I guess if there's a way you do it, there's a way you do it, right? Wait, nx doesn't go up here, right? That's the difference. Let's just continue. There it's nx. All right. Oh my God, dude. I'm so scared. Okay, so we do that. All minus equals all digits equal. This guy really, he's going for minimal source code length. You got to respect that, right? You got to respect that. That's not how we play things here, though. It's counting leading zeros after the decimal place so it doesn't waste mantissa precision on them, but only if there were no non-zero digits before. Right, that makes sense. Yeah, I get it. Okay. So we're going to return the string as well, because this code seems to be doing that. Although, what's stir? Stir is just the input? Yeah. We'll just do that. Turn the input. Okay, if it's an E, we're going to leave it that way. That's kind of nutty, but we're going to leave it that way. And then we make another pointer Q that we're zooming along. We're zooming along. This is all right. It doesn't want to go where I want it to go. That's fine. Go to. I never even did go to, guys. Okay. All right. Okay, D is like not even used except inside this if. So that's weird. Right, so like Okay, we're going to go. This is really a lot like the other code. Okay. Okay, so if after the plus or minus or the E, it's exactly like the other code. This has been a weird repetitive day. So D, all right, N is Q plus 1. D is the decimal value. D equals S sub Q minus 0, right? Okay. So I actually don't understand. Like, this is redundant with this, sort of. I guess. I don't know. Maybe if you tried to factor it apart. All right. So while. Maybe I should make an is digit so I don't keep typing this out. You might have actually had one. So while S sub N. I so made mistakes here, guys. Probably. Okay. Wait. Wait, we don't use Q in the loop. Right. Okay, it's fine. It's fine. All right. Okay. And then if we have no digits, this is exactly, dude, this code came from the other code, or that other code came from this code? To some degree. Somebody was like loosely cribbing off of somebody else, because it is, or they both came from some old Fortran code. I don't know. But it's like the same thing. I even have to write my same comment here. Remember that when I typed this like 6 hours ago? Okay. In range. If let's check. I don't know where that's defined. This guy uses this function a lot. I don't know what that one means. Let's define it. Huge val. Is that supposed to be? That's supposed to be infinity, just like before. Oh my God, this is the same code, guys. This is the same code. Okay. Earlier loop, your continue won't increment n like the for loop did. Oh, that's a good point. I keep wondering if we should add a little bit more in terms of like while loop feature or something. Like I find that it doesn't matter for me when I'm programming enough to do anything like that. But when I port code that uses C++ for loops, it does. Like this is like tweaky and weird and like not good, right? So maybe we should add something. It's just like I just never use it when I program. Maybe that's my own stylistic thing. I just never need it. Okay. Okay. We don't have count leading zeros. Wait, isn't bot U64? Yeah. So we're just going to go there. Count leading zeros. Whatever. And then we're finally here. Which, like, what even did we all just do? Okay. We'll get to the bottom and then we'll return 0 remainder. We can at least make sure that we like parse out the things and whatever. Count leading zeros is just BSR plus a subtraction. I mean, there's probably, I don't know what BSR is. Something shift right. But Hacker's Delight probably says how to count leading zeros. Bit scan forward. Yeah, we don't have that either. Oh, bit scan reverse. See you later, Sean. Is there no x86 intrinsic for counting leading zeros? Yes, there is. We just don't have access to it, bro. That's what I'm saying. You don't magically are able to access every CPU instruction from your new programming language unless you do that. And it's complicated. We can write it though. We're going to make it really stupid. We just want this to work right now, right? And then we would test it later. So, n return n while x and mask n plus equals 1. No, while not n x and mask n plus equals 1 mask right equals 1. All right. So now, of course, when we shift mask down to 0, you will not get x and mask, so we will infinite loop. So rip. Although we probably won't usually get there, right? So we're going to say like that. I mean, I guess I don't, right? Tell me how much I messed that up. Wouldn't that be the kind of code that is ripe for a macro to... No. Okay. Let's see if this even compiles. I guess I never did. Left equals. I think I just decided. So D. Oh boy. In range. Whoops, don't compile the game. Xmin. I don't know what that is. It's probably not in the file, right? It's probably in. It's probably in D-A fast.h. D-A fast.h. Nope. Dota, the guy plays Dota. What header file do we think these will be in? It's probably in the frickin' M, whatever the hell's map M. Okay. Bias 1021. We did that before. Really? Okay, we did all this and we really are not testing any of it. Let's try some things. Let's try our count leading zeros. Oh, 7, 1. Right? Should be 9. Nine. We did it right. We did something today, guys. Well, we fixed a lot of bugs in the game this morning, but we did something today now. Leading 0 is 9. That's great. And then if I do U64, it should be 41. It's 41. Boy, it's very grindy to hand convert code from C, especially when you started over like 3 times with different people's code. Like this wouldn't have been that bad if we just went straight here. But the fact that we were doing the other thing for a while and then being confused about things, and we're not even done with this. We haven't even done like the actual part. This is just the pre-pass. All right. So we should be able to call stir to D fast, and we'll get back 0, but we want to see what the remainder is. All right. So okay. F remainder stir to D fast S all right. Well, we correctly found the end of the number, so we didn't screw that up. What if it's there? What if it's there? What if it's... Wait, you can't have a decimal point in the E. Well, it even did the exponent is too high and returned infinity correctly. So this is pretty good. Like it maybe works so far. Yeah, no, C++ does not set uninitialized stack variables to 0. That is not a thing. They're simply uninitialized. Uninitialized global variables get set to 0, like in the data segment. That is in the spec, but stack variables do not get initialized in C++ in that way. All right, this is a good start, kind of. So now the problem is we need the other part. So we have started efast, and that calls this guy, who is, wait, is that who that calls? Yeah. Who is not that big. We might actually be able to get something done tonight. Okay. So like that. Sturdy Kivit. M is a U64. Bot is a U32. Bex is an S32. I is an S32. Neg is an S32. Okay. Bots. All right. Then we do mol96. Okay, so then we say like that. Oh, wait. Okay. I is minus bx, bx was 0. Tail is n1 left shift 32 or n0 right shift I. Sure. Okay. If n1 let's put some braces here. Okay, fix OX400. That's something. And then hex double. Great. I don't want hex double. What is this? U.U. The hell is that? And why are you using so many parens? Turn U.D. Oh, this is just casting into float. Let's do that. Okay. So we're going to do that. Whoops. It's not a struct, it's a union. throw. That's a hex double. U dot U64. Okay. We don't have fixes. Oh, God. This dude likes doing this stuff. Procedure only returns 3. Okay. No, that's not right. All right. So I'm confused by this because N0 is right. That. I guess. Why am I casting to U64 there? Wait, if this is 32 bits, I'm casting to 64 bits and then right shifting by I. That doesn't do anything. Why is that cast there? Can anyone tell me why that cast is there? I think that's just a mistake. I think that's a mistake. Signedness? No, it's unsigned to begin with. Is it because BXP is large? BXP isn't there. I'm just talking about this. I don't know. Variable BXP is used. Oh, right. I goofed. But it doesn't like that. How is bot U64? Because we declared it that way. Okay. Okay, so we need these. Fix. It's not in mapm. Oh, it's these. So this is the rounding hackaroonie, hackazino. Let's, there's no reason. Like, these are only called once. Oh my God, he's using not. If n0 is equal to 0, n1 minus equals 1. That's like literally... Okay, let's like leave this. Okay. If n0 is greater than whole. Oh my God. Not. And then added to an integer gives you 0 or 1. All right. So like if n1 and 0x800 r plus equals 1. All right. Whole. That's probably from the other thing. 98u. Oh, there's no R. It's there we go. Okay. Well, we did all that to get a 0, which doesn't sound good. Are we calling this? Yes. Crud. Okay, we got a number. It's just not a very big one. Arithmetic shift versus logical. It was already unsigned. It was already unsigned. I mean that could be reasonable. Let's do them in the other order. That's our convention. Okay, so we come in with just one number, which is, I guess, plausible because our number didn't really have that many significant digits. I don't know. I don't know how that works. We get a bigger number out. This is just not nearly a big enough number to be a reasonable float, unfortunately. Okay, neg or bexp. This is weird. Because that should make this a much higher number than it is. bexp is 1059. So all right. See, I don't understand this. Specifically, so upper, we're getting a 32-bit number. But we're supposedly casting this to U64 and left shifting by 52. So there should be a lot of zeros to the right of this. Right? Is my cast precedence messed up? I think it might be. Yes. Oh, dude. Cast is lower than bit shift? Okay. Cast is lower than bit shift. That, we need to think about that. Or I feel like cast should be the highest thing. You know what I mean? I got the first half wrong. Well, I have to audit the whole program for this now. Like this, right? And this. Like everything we did today doesn't necessarily know this. Like really? Who knows, people? Still zero. Why is that printing as 0? That doesn't feel like it should print as 0. On the first line I fixed, I got the first half wrong. The first line, I don't know what the first line I fixed is. This one? Oh, okay. That is not the correct floating point number. Oh, maybe it is. No, because times 10 to the 12. Let's take out the E for now. That is exactly 2 times the correct floating point number, right? So if we multiply it by 0.5, we succeeded today, guys. After all this, after all these many hours. All we have to do is just tell everybody, whoever writes a program in this programming language, when you convert a string to a float, remember to divide the float by 2 afterward. Right? Okay. The good news is the problem could be almost anywhere. um, Okay, so my idea is we can tell if it's in the first Tangler we did today or the second one by the following method. When we call this Kavut routine, we just don't do this. We're commenting this out. Okay? And so wait, what does that do? That just doesn't multiply by 10 to the... Wait, that's not going to help. Here's what we do. So like the problem is Bx was 1 too high, right? So instead of this, we should be able to do this. Yeah. So the question is now, why is bx1 too high? Well, it has to be somewhere that sets bx, right? And it's not here. I don't think that sets bx to 0. That's not there. So yeah, that works out here. I would assume it's in the input up here, honestly, if I'm being honest. So bx, oh, that's the whatever is the fourth argument. Bot, no, sm bot lz. Okay, this whole lz, okay, that's still right. And if I comment that out, it's wrong. So does this mean m is one digit off, or that our hold on. Digits 8. So we're going to this default case. LZ is 37, right? So we're getting the wrong answer now, though. So M before is whatever. Format int M base is 16. And then M after that is shifted to the top of the number. So that's a correct count leading zeros. Now I assumed that that meant that the LL meant 64-bit. I mean, I should look that up. Mapmclz.c. Oh my God, what? Okay, this is like some crazy binary search CLZ or something, right? Oh my God, guys. This is straight out of Hacker's Delight. What a cute way to compress your table. Okay. I would rather just use CLZ instruction. Oh, whoever said it was a bit shift right, there's a bit shift right there. But like, look, I don't think it's off. You know, our CLZs could do this though. You just say, right? And then we don't have to check because the mask will never go to 0. So that gives us a faster loop, right? I mean, not that we're going to replace this with an instruction later anyway. The original code had a go to, yes. So that go to was here where we say skip equals true. If not skip, we do this stuff. Okay. But we do. Let's just print down here. LZ is still whatever. Whoa. Oh no, because we set it here. Did I type in the bias number wrong? Okay, so it sets 1048 and it's still 1048. So this doesn't happen here. $10.21. $10.21. I'm getting tired, everybody. Hi. We are off by a factor of 2 somewhere. Let's try some very simple things. What if this is 1? Then it's not off by a factor of 2. Okay. That gives us information. 2. 4. 8. 8.5. We're counting the decimal. Okay. We're counting the decimal as a frickin' digit. I messed this part up. One dot oh, yeah, that'll be 2. We'll do it though. That'll definitely be 2. One dot is 1. So it's really the O. It's really the O that multiplies you by 2. Didn't you know that? Didn't you know anything about this? So it's this other loop. I converted it incorrectly in some way. Oh, well, actually, I mean, there's also this, sort of, but that's supposed to increment LZ. I don't know. Okay, what did I get wrong here? Let's go back. We're just looking at the code. Oh my God, this code. Okay. Yeah, it's not this part specifically, because if we do, if we do 1.1, it'll come out to 2.2. It's really not that part. So all digits is LC's. Right, if I do that, does that? Whoops. No, that's not right. So this is, okay, look. I am very grumpy about a certain thing. LZ, early in this code, stands for leading zeros, which means the number of zeros that are written in the string before you start getting to significant digits. They're decimal digit numbers. Down here, it's a totally different thing. It's the number of binary leading zeros in the top of the frickin' binary number, bro. Like, who does that? Me before I was out of college. That's who does that. Okay, we're going to make a new number. Okay, see, it's really weird because it gets set either here or here. So the old value does not survive. Let's make it a new. I mean, this is a big number, but we're big. Okay, so this makes it pretty clear. See, I got confused tracing it up. This makes it pretty clear that the problem is that M is actually off, which is very weird. So like, if I go like that, wait, what? How did I get 1.2 out of that? Whoa, now I'm confused. Oh, before, we got to do it after this, right? Minus equals 1. Okay, great. So this is correct. 64 plus bias minus binary leading zeros. So if we add 1 here, still correct. So we have a sign toggle. Like, see, this is a different, this isn't binary leading zeros anymore. This is something else, right? This is, we'll call it bexp to be consistent, right? So bexp is this, and bexp is there. Okay, so this is bothering me, man. Seems like CLZ64 must be off by 1, except we tested it and it isn't. See, it's B. This is 4 bits. That's 60 bits. And then we shift it to the right place. So maybe the problem is after that, right? Maybe the problem is actually here. And we're just making up for it, right? I mean, the problem could be in mul 96. You know, it could be in mul 96. Because remember, that was the thing that wasn't in the table, and you do some math. Like, what if this just isn't precise? Or normalize does the wrong... all right. Normalize What frickin' file was it in? This one? Normalize. Let's look at this again. I don't think we will. Oh, actually, we might. So this adds 1, by the way. So this could be annoying somehow. This could be annoying somehow. Now, if I wanted to compile a C program, I could just do that. It's just compiling. It'd be annoying because I'd have to put all this mapm stuff. I don't want to include all of it. You know, like, bleh. I'd have to start embarking on C. But we might, if we could do that, we could just step through and see what's different, or if it actually works. Maybe it's wrong in C for some reason. This could also be wrong in some sense, like if we don't shift bx enough, although if it were odd though, that would cause problems. Right, but if I do this, if I do bx minus equals run right there, we get the right answer. So like it really could be anywhere. Mostly. I was trying to limit it, but so bot is large. I don't think it'll be. It's not. So it didn't go through either of these. I mean, we could double check that, but I don't think so. Really, most of this code doesn't actually do anything in this case. Just run two debuggers and step side by side. Yeah. What did we do wrong here? What did we do wrong here? Is there anything for web programming that I like? No, I do not like web programming. You thought you figured out that the parser was counting the dot as a decimal place. You know what? We did figure that out, didn't we? And then I forgot. We literally did figure that out. Thank you. We knew that. I mean, we could verify that some more, but right? So, like if we say 1, 2, 3, right? Oh, well, hold on. Let's get rid of my hack in here. All right. If we say 1, 2, 3, it's correct. If we say 1, 2, 3 dot, it's correct. If we say 1, 2, 3 dot 1, it is wrong. We knew that. I'm just tired. We knew that. Okay, so like, I just don't understand how that happens. Right, because I started looking at like, oh, maybe digits is wrong or something. Or maybe LZ is wrong. And that's when I got confused because this was a different LZ than the other LZ, bro, which was, Okay, so the problem that I have looking at this code is I don't understand how it could be off by a factor of 2 because these are factors of 10. So like, how could having a character after the decimal result in a factor of 2 problem? But it is in here. Because look, if we just delete the period, right? If we go from 123.1 to 1231, it's correct. So it's literally the presence of that is causing us to be off by a factor of 2. That is so weird. I guess it's maybe even this, right? No, it's not that, because okay. So nexp, right? If we tweak nexp, we're going to be off by a factor of 10, right? Yes. So it's not nexp that's wrong. All digits doesn't matter, probably. Like the... I don't get it. It's like M has to be off by a factor of 2. That's the only thing, right? Right, is that? Wow. But if we shift it off, we kill... Okay. There's like some kind of log base 10 divided by log base 2. You know what I'm saying? Like... Or binary leading zeros is off. But it's not. Well, you got it building. For 1.0, it calls stir to deconvert. We can check that. Let's check those numbers. Thank you. That's helpful. So we're going to go down. We're going to change this to 1.0. 1.0 hello sailor. All right. Print M is this. Actually, it's printed in here, right? M is this. Bot is this. LZ is this. I think LZ is 1025. Sorry, BXP is 1025 because we're printing that out, so that part's correct. I is this. Neg is this, right? So M format int M base equals 64 or 16. Bot BXI neg. All right. Okay. A with a bunch of zeros. 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 16. Bot 0. LZ 1025, I minus 1, neg 0. Okay. Those are the right numbers. Before calling mol96 bx equals 1025 and after bx is 1021. Ours is not 1021 after. Ours is 1022. So the problem is in mol96, bro. That is so weird. How does it have to do with a decimal point, but the problem is in mul96? I assume that meant because of a parser, but what it really means is we cross 0. If we cross 0, we're off. So maybe there's a way that our rounding is different from... Is our rounding different from C? I is -1. I times 108,553, right shift 15 is -3. I feel like that's going to be different on your end. I feel like that's going to be -4 or something else. Do I need to put parens around the casts in mul96? I don't believe so, but we're going to be paranoid. I don't think that'll change anything. Okay, wait. My BX after that I'm printing. All right. I equals -1. Delta is -4. So you mean here. Okay. Does anyone know what cast comma trunk U32 means? No, nobody knows. How am I getting -3 and C is getting -4? This seems like a straightforward... Are we just saying that we're getting different answers for this? Is that literally all we are saying? -108,853, right shift 15 should be -4. I think... Oh my God, dude, what? How is right shift not lower precedence? What? Hello, rating people. Okay, this is just a bug. Like, what is going on? Oh, you know what it is? Okay, this is a bug in constant expression evaluation. It's not actually operator precedence. Oh my God. All right, I deserve. See, this is why we do these things, because we find these problems. I bet the following thing works. The following thing works. This is what you get for working on a programming language in development. I'm going to say A is an S32 is 108853. And I'm going to do this without parentheses. I bet you that gives me the right answer. No, it doesn't. Okay, I was wrong. I admit it. Wow. What? So we're saying that we're doing this. How is that happening? How is that remotely? How have I been going for years programming in this language and not got burned by that if that's a bug? Can somebody please explain to me? Yeah, thank you. That was super helpful. I don't know how many more hours I would have spent trying to find that. So maybe that cast problem that we saw is related as well. I usually use parentheses around everything. I was just trying to loosen up a little bit, and the loosening up maybe has revealed that there was a bug. Should have used Docker. Well, maybe. Every day feels like, how the hell has this worked for how long it has? Oh, I've had that feeling before. I know that feeling. Fortunately for me, it's not every day. All right, guys, we have a float to, or a string to float parser that is not frickin' libc. We have to copy over the copyright and attributions, and we're gonna want to clean up all these frickin' printfs and test some things, right? And not accidentally delete actually important code while I delete all the printfs. All right. That was super helpful. So, you know, sometimes Twitch chat is really annoying and awful, but paid off right there. Paid off right there. Okay. Bam. What's the bug? That expression isn't obeying operator precedence rules. Yes. You would expect bit shift to be lower precedence than like times, right? Maybe for some reason I decided it shouldn't be, but that seems weird, doesn't it? Also needs a shootout versus MSVC. Yeah, well, for sure we can time it, right? So the next step, after getting all this cleaned up and maybe bug fixed a little with some of this crazy stuff, let's delete all this. It's so weird that that was the bug, but it only exhibited when we had a decimal point followed by a number, even if the number was 0. Like, what? That was really strange. It made it look like a parsing bug, but it really wasn't a parsing bug. Okay. Okay, so this does not have the super, super pedantic behavior that people seem to want in very rare cases these days, but it's basically right for almost all the time. And if it's off, it'll be off by 1 ULP for pathological inputs, which we'll just decide what to do about that later. Okay, we're gonna put this stuff aside in case we need it sometime, but I'm gonna hope not. Oh boy, it's mostly table. We love tables. All right, thanks to Ubrik, or however you pronounce your name. That was that saved me some good time. We might not have finished tonight because I'm very tired now. And I probably, yeah, it probably would have taken later. Maybe they have the same precedence, but it's left right. Yeah, I don't know. That's just going to have to get investigated. That could be driving people nuts, honestly. I really don't know. Like, okay. It's like, how is that a thing? Get binary operator precedence. Okay. Minus, I guess, is supposed to be tighter. So times -1. So wait, what? It was times and right shift. So right shift is supposed to be 3. Maybe our test is just reversed. But if it's reversed, oh wait, no, it is. It's just whack. Because, okay, higher, I guess, is supposed to be tighter. Because times is tighter than plus, and I know that works. I hope that works. I hope that works. Y is 3 times 4 plus 5, right? Okay. So that is right. So we actually, for some reason, decided that bit shifts are actually really tight. And I don't think that doesn't seem right. Why did I decide that? C++ is 5 for multiply, 7 for shift. Wait, does that match C++ then? Or is it lower is tighter for, what is plus for C++? So higher is looser in C++. So I do have shift in the opposite precedence, which also explains maybe why the cast was having problems, right? Like, I don't know how cast actually that's evaluated elsewhere. Yeah, we've been streaming for like 11 hours today. I did it for that dereferencing a pointer. Um, I mean, this is binary operators and unary operators have like different numbers actually. They're unrelated. So that part doesn't matter. Okay, I need to changing that will be a little bit of a pain in the ass, but you know, all right, everybody. It is definitely time for me to go to bed. Thank you for coming by. Thanks for helping with the thing. We have made good progress today. We fixed game things in the first stream. Our Benny test goes real fast. We've got a profiler from yesterday. And now we have numbers. All right, thank you, everybody. See you later. See you later.